Lo stage live YouTube. Lo stage live YouTube.
attivo la mia camera perché non ce l'avrò, restiamo insieme. E poi basta, tu dici quello che vuoi, io sorrido.
Sì, ma in realtà
e poi basta, la mia camera perché da dopo restiamo insieme.
tanto comunque io penso di dire due minchiate solo. Ah, che bello, siamo tutti qui, e basta, più o meno questo è il senso. Cioè non ho pensato a un vero e proprio discorso.
La mia camera perché da dopo restiamo insieme.
Tanto comunque io penso di dire due minchiate solo. Ah, che bello, siamo tutti qui, basta, più o meno questo è il senso. Cioè non ho pensato a un vero e proprio discorso.
Hi everyone, welcome to e-Rum2020. We are here, we made it.
Yeah.
Okay, I'm Maria Chiara Fortuna. Great. I'm Maria Chiara Fortuna, I'm the chair of e-Rum2020.
And I'm Francesca Vitalini, vice chair of e-Rum2020.
Okay. We are here to give a short introduction about e-Rum, about Opin, the platform that we are going to use. And then we will have the official welcome from the organizing partner and organizers of this conference, and a short introduction of the schedule of this day. So I will now share just my slide. Okay. As you know, e-Rum is a biennial conference that brings together our users and experts from all over the world, but it was born as a physical event hosted in the city of Milan, in the University of Milano Bicocca, and in Politecnico di Milano, and with the patronage of the Milano municipality. But in February, when we had already finalized the program and opened the registration, the coronavirus epidemic changed everything. On March 31st, we embraced the adventure to turn this conference into a fully virtual event, the first multi-day conference completely online. Today, we're about 150 people on stage between speakers, chairs, and organizers, and more than 2,000 attendees from all over the world. We can say that this choice made this conference more inclusive and really open to everyone. When we decided to turn the conference into a virtual event, we decided also that we wanted it as similar as possible to a face-to-face meeting. So we started to look for technical tools that allowed a virtual full experience. So with the navigation bar on the left, we can move between the areas of the conference. The first area that you see is the reception. In the reception, you can see the areas active now and the full schedule of the event. You can also find some Opin instructions, similar to the one that I'm seeing right now. If you have troubles with Opin and you need support, we have a Slack workspace where our technical team can help you. The link is on the chat. Here, where I'm now, is called the stage. The stage is the equivalent of a plenary area of a physical conference. During e-Rum, the stage will host our main guest, the conference keynote, and invited speakers. The session area hosts parallel rooms. There we will have all the parallel sessions, namely regular and lightning talks, shiny demos, and poster session, plus individual rooms for meeting the speakers. I will cover the Q&A topic better later. In this area, we will also have rooms where you can join the conversation with your video if you want. The thematic lounges, conversation during lunchtime dedicated to specific topics, the open lounge for random chatting, and our sponsors' recruiting sessions. Going down on the bar, you can see the networking button. If you go there, you are matched with another random attendee from the networking area, and you can start a face-to-face conversation. But don't worry if the person is boring, because the conversation will last only 4 minutes. After 4 minutes, the person changes and another one-to-one meeting begins. The last area that we have is the expo area, where you can find and meet the conference sponsor. It's thanks to them that this conference is free and open to everybody, so I really wish to thank all of them. In the expo area, you can meet the representative of our sponsor and see their demos and offers, so be sure to check. Now let me introduce the team behind e-Rum, the e-Rum organizing committee, the group of people that is sharing with me the adventure of creating this conference. So I'm really happy to leave the stage to Francesca, a pillar of the organization. Francesca is now on maternity leave, but she should be able to join us for a while to give her welcome.
Yes, indeed, I made it. So it's kind of a second baby getting born with e-Rum. So I really wanted to be here. And I want to add my voice to the one of Maria Chiara to thank all our sponsors for making this event possible. And also the organizing committee who put in so much time, effort, passion, and endless neurons burned to make this happen, especially because we had to recreate an entire event again for the virtual version of it. But in the end, this was all possible because of you, like the community that gave us the support and the motivation to make this event happen. So I would like to ask you to join me in a big round of applause for the entire community, because we made it, we are here, and e-Rum is finally happening. So thank you so much.
Thank you, guys.
So I give the word back to Maria Chiara so we can proceed with the event. The real stuff is happening now.
Thank you, Francesca. Thanks to Sofia that allowed your participation here. She's very, very small. Okay. So let's move to the other organizers that we have. So I'm here also as a representative of the Milano Art Association, the association which is behind e-Rum2020. But I really want to introduce on stage the opening welcome of the assessor Lorenzo Lipparini. The city of Milano gave the patronage to this event, so we can leave the stage to the talk. Okay. Okay. We have the video of his welcome speech. Okay, maybe we have some technical issues. Okay, great. That's good.
Good morning to everybody, and welcome to the art user community of Europe. I would have said welcome in Milan, but I can just say welcome from Milan. We were supposed to meet here in my town, but due to the health emergency, it's only possible to meet virtually. However, there is a lot of my town into the program of the next days, and that is thanks to the organizers of this event and to the two universities that work to the program, the University Politecnico and the University of Milano Bicocca. In Milan, we have 8 universities, a huge number of students in Milan, and we are working with the municipality of Milan, with most of the universities, on special projects related to data visualization and data science in many projects, European projects, hackathon and activities to ensure proper work on our public patrimony of data. The municipality of Milan gave the patronage to this event, and this is why we believe data are very important, not only for communicating what we are doing, but to organize a proper participation of citizens to the decision we have to take for our collectivity. I am Deputy Mayor for Participation and Open Data, and we decided to keep these two teams together because there is a proper participation only if we work properly with data, knowledge, and information to give to the citizens. This is why we decided to have special projects with data. And you can now visit our open data portal on dati.comune.milano.it, where we have not only raw data, but you can also see special projects made by dashboard and visualization on most issues important for our town. You can find a special project on budget. That is a project we worked on also with the art community in Milan, but also special projects on sustainability, on economy. And tomorrow we will publish also a special project with all the data and the visualization about the management of the municipality of Milan in this special period of health emergency, around the activities made due to this COVID emergency in Milan. We also have a Geoportale, which is a website where we publish all our maps we publish all the open data related with maps, and you can find information about the streets in Milan, the houses, patrimony, the trees, the green area, and also the history of our town. That is on geoportale.comune.milano.it. It is very important because it is a particularly easy way to look at the data and the public patrimony of data of the municipality. But I think that is very important to deal with these matters, and I expect this conference to explore many ways of working with data and data science and visualization to make the data stronger for the general public and for experts, and to have more value out from the data. Should you need to plan your next visit to Milan, and I hope to meet you soon in a new occasion, in a different occasion, I leave you with one last website, which is www.yesmilano.it, where you can find all the information to plan your trip to Milan, or on cultural event, on our patrimony in Milan. You can find many information about our town. So I hope there will be a new occasion in the next months, and I leave you wishing you all the best for this conference, and enjoy the next panels, the next days of the conference, and hope to see you soon in our town. Bye bye.
Okay. Okay. Now let me call on stage Matteo Pelagatti, the head of the Department of Economics, Management and Statistics of the University of Milano Bicocca. Okay, thanks, Matteo. Bicocca was the hosting university of the physical event, but now it's actually hosting also the headquarters. So we are sharing almost the same background. So I leave the stage to you.
Thank you, Maria Chiara. Yeah, this should be the place. This should have been the place where we had met, but it went another way. So I'll just welcome you virtually here and share my screen. This. So just 4 slides actually about Bicocca. Bicocca is a very recent university. Actually, this is the place where we should be talking right now, and actually not right now, 3 weeks ago, but this was our whole room, or aula magna, as we say here, or auditorium, whatever. And we should have been here, but things went differently. We kind of become the center of a disaster. But anyway, so what's Bicocca? Bicocca is a university who's like 20 years young, and in these 22 years has achieved a lot. We have 33,000 students. We have 14 departments, 8 of which are being declared by the Ministry of Education like excellent department. I think it's the highest ratio in all universities in Italy. Then we have 800 faculties and 1,500 faculties, researchers, postdocs, lecturers, and so on. And we offer so many programs as bachelor's, masters. All masters are 2 years, masters, and 16 PhDs. So just a few numbers that describe Bicocca. There's a very high research output in this university. We are very high in citations and these kind of things. But the most important thing is that we are very much committed to data science and R. In fact, we have R and data science, some different interpretation of data science in 5 courses to our bachelor's and 3 are master. 3 years ago, we came up with this data science master, 2 years old, 2 years master, which involved many departments, mainly my department, which is the Department of Economics, Management, Statistics, the Department of Statistics, and the Department of Computer Science, but involves many other departments for applications. And then this is a very recent news. In 1 year, or a little bit more than 1 year, we will be offering also at least the Bachelor in Artificial Intelligence together with the University of Milan and the University of Pavia. And other than that, we're also teaching data science and R in particular to high school teachers. We are trying to move like also high school education to a data science level. And also, of course, our colleagues in Bicocca, which may be not acquainted with R and data science, and that's our main goal at the moment with data science. And of course, there's many research projects which we don't have the time to talk about here. So let me just end this presentation and thank Maria Chiara, Francesca, and the whole team. They did a great effort, and I'm certain we'll see a great job done in this conference. Of course, all keynote chair, panelists, and all participants to this great event. So please take the word, Maria Chiara.
Thanks, Matteo. Thank you very much for your introduction and for your words. And so now we will have another official welcome from Professor Giulio Magli, the head of the Department of Mathematics from the Politecnico di Milano. So now we will see his official speech to give you the welcome here.
It's really a pleasure for me to welcome you in Milan for this meeting. Of course, we are obliged to have the meeting in a virtual way, so it's quite a virtual welcome of all of you in Milan. But I really do hope that every one of you will have soon the occasion of visiting our country and our town in presence in due course at the end of this horrible pandemic state. For the moment, really, let me virtually welcome you, and I'm very happy to have the occasion of introducing you to this conference, because it is quite an unusual and interesting conference in which many aspects can be analyzed, and many people are coming from different areas of research, but also of application and commerce of such an important statistical tool can meet and discuss and produce new ideas. For us, it's a special pleasure to be among the organizers of the conference because Politecnico Milano is and in particular my department, which is the Department of Mathematics, is really deeply involved in research in statistics, and R is a fundamental tool in such research. Let me just mention that an important part of our degree program in mathematical engineering has applications in statistics, and of course we have also 2 PhD programs, of course in English. One is especially devoted to data science, and the other is more traditional, so to say, PhD program of mathematical method engineering, which also has a relevant part on these issues. So for such reasons, it's really a pleasure for me also to thank my 2 friends, Pier Cesare Secchi and Pierluca Lanzi, who were among the organizers, together with all the heterogeneous committee who has made possible to have in Milan, or virtually in Milan, the conference you are going to attend. So I think it's enough. I think I want to wish you a fruitful and pleasant virtual but also practical in contents conference.
Okay, so I will share again my slides with you to give the official start to the first day of the conference. So this day will be very dense of content and will be slightly more focused on art in life science. I'll go very quickly along the program that we are going to see today. So this is the morning. During the morning, we will have the first session of invited speakers, where we will have Britta Welton and Edwin Toen, plus the 2 COVID winners, Manuele Guidotti and Mark Hanley. Then we will have the first virtual break, where you can meet our sponsor and explore the expo area. Then we will have the first lot of parallel sessions, so the regular talks. The first one will be focused on machine learning topics, and the second in art in life science. During lunch, we will have a thematic lunch with an open discussion about developing software and careers in life science. And you can join this conversation if you want. We will start again in afternoon with the first keynote speaker of the conference, Stephanie Hicks, that will be on stage. Then we will have another virtual break where you can meet the sponsor. The third and the fourth parallel session, the first one about our application and the second about our life science. And then the last keynote of the day, Jared Lander, still here on stage. Remember also that from 3 to 4, we will have the synchro recruiting session, and the sponsor exhibitors, the networking area, and the open lounge will be always active. So if you want to interact with our speakers, remember that there are different modes according to the type of talk that you are listening to. During the keynote session, you can propose your question using Slido, and a link will be pinned on the chat. Regular lightning session will be closed with a panel discussion between the session speakers. So if you want to propose your question, you can write it on the chat on the right side, or you can directly join the conversation with your video. After the invited talks, the shiny demos, and the poster session, there will be individual meet the speaker rooms where you can join the speaker and ask your question in person. Finally, don't forget that we will open and close each day with a yoga session, so be sure to participate. So, okay, now we can have a 10 minutes break, and we will start again at 9:40 here on stage with the first invited session of e-Rum 2020. So see you soon.
Good morning, everybody, and welcome to the very first session of e-Rum2020. My name is Mirko Signorelli, and I am one of the members of the organizing committee of e-Rum2020. And in my daily life, I work as biostatistician and R programmer at the Medical Center of Leiden University. Actually, the fact of being a biostatistician who works with R is the main reason why I'm going to chair the first invited session of today, which will focus on 2 of the 6 tracks that compose our program. The first track that we will cover in this session is about the use of R in analysis. The second one, so R word. We have a lineup of 4 interesting talks for this session. So what will happen now is that I will invite each invited speaker to come on the stage and present their work, exactly in the same way as it would happen in a non-virtual conference. Each talk will last 15 minutes, so in total this session will last for about 75 minutes. At the end of this session, each speaker will be available in a dedicated session for 20 minutes, and there attendees will be able to engage with the speakers and ask them questions. Now, without further ado, I would like to welcome on stage our first speaker, Britta Welten. Britta is a postdoctoral researcher at the German Research Center, where she develops statistical methods and computational tools to integrate multimodal data for a better understanding of complex biological systems. Hi, Britta.
Hello, everyone.
So the floor is yours.
Yeah, it's really a pleasure to kick off the first session here at e-Rum2020.
It's a pleasure to have you here.
I'll share my screen. I hope you see everything. So in my talk, I would like to show you some R applications from the life sciences and present you one package that we've developed, multi-omics factor analysis, that we use as a probabilistic framework for the scalable integration of multimodal data. So why are we interested in multimodal data? Working in life science, we basically aim to understand the molecular mechanisms that underlie the functioning of an organism. For this, we have to study diverse classes of molecules that make up the cells, which in turn are the basic building block of every living organism. And thanks to recent technological advances, we can now use modern technologies to get a comprehensive quantitative characterization of a given class of molecules, and the resulting data is often referred to as omics data. If you've never worked with omics data before, you can just imagine it as being some large, typically very high-dimensional data with molecular features measured in a set of samples. However, often a single omic is not enough to really understand a complex biological process, like, for example, a disease such as cancer or a developmental process. Here, multiple molecular layers play together in shaping such a process, and therefore we also have to study multiple omics jointly in order to get a comprehensive understanding. And that's where multimodal data comes into play. And just to give you one motivation where this is of importance, let's turn to clinics. Here in clinics, the heterogeneity across patients in terms of disease onset, disease progression, or treatment outcome is still a major challenge because it makes it very difficult to decide for the optimal treatment of a patient. While some patients respond very well to a certain drug, other patients do not respond to it or suffer severe side effects. And with multi-omic approaches, we hope that we can gain a better understanding of this patient-to-patient heterogeneity and eventually enable personalized treatment decisions on a molecular basis. However, working with multi-omics data can be really challenging. First of all, there's usually a collection of very heterogeneous data as it were measured with different technologies and therefore also come along with distinct statistical properties and an inherent structure that is given by these different molecular layers as well as by different sample groups that can, for example, be different age groups of patients or also due to the experimental designs, for example, some samples that were treated or samples that were not treated. In addition, the data typically displays complex correlation structures and hidden confounders can impact our measurements, which we are not aware of. And due to the sheer size of the data, we need to make sure to use appropriate regularization strategies and have algorithms that are also scalable to large data sets that can contain hundreds of thousands of molecular features or samples. And finally, there's also often a lot of missing values in the data, and we want to have interpretable approaches so that we can later on go back with our results to domain experts, biologists, clinicians, and together have a look at the results. And in order to tackle these challenges and facilitate working with multi-omic data in the life science, we built an R package called Multi-omics Factor Analysis that is based on the Bayesian model for the unsupervised integration of multimodal data. So the basic idea is that MOFA performs a structured matrix factorization to infer a joint low-dimensional representation of multimodal data. So this is displayed here on the bottom. You can see that we have this complex data set that is structured in the different molecular layers, which I also call views here, and different groups that correspond to distinct sample groups. And we jointly decompose it into a set of latent factors that is shared across all molecular layers and weight matrices that are specific to each of the molecular layers. And as the different molecular layers come with different properties, we also implemented different noise models for each of the views so that we can choose the noise model for a view that is most appropriate for such data. To ensure interpretability of the approach, we use a range of different sparsity priors, both on the factors and on the weights, such as the automatic relevance determination prior and the spike and slab prior, which makes it easy to determine for each factor in which of the molecular layers this is important and in which sample groups it's important. To ensure scalability, we base the inference in this Bayesian model on a stochastic variational Bayes approach. And the algorithm for the variational Bayes approach is actually implemented in Python. And we've used the reticulate package to interface this back to our AR framework, which works really nice in our case. And to make sure that researchers can also input their data into this framework easily, we interface with a range of different bioconductor and R classes, such as, for example, multi-assay experiment, which is a really nice container for such multi-omic data sets, or Sera, which is a popular tool in the single-cell field. So once a model is trained, we, of course, want to understand what these factors are actually about. And for this, we have a range of different downstream analysis functions implemented in the package, which are also available in the Shiny app, where people can just upload their trained model and then explore the results in an interactive manner. So first of all, what we typically do is to see which of the factors explains variance in which of the views and which of the groups. So such a variance decomposition often gives a very clear picture thanks to these sparsity priors we put onto the model. So for example, in this case, we would see that the first factor is only important in 2 of the sample groups and most important in 2 of the molecular layers. Next, we can, of course, use the factors to visualize our samples in the latent space. For example, here we see that in the latent space spanned by 2 latent factors, we see a nice clustering of the samples in 3 distinct groups. And then at the end, we, of course, also want to get to the molecular signature of the factor to see what biological process is actually captured by the factor. And for this, we can look at the weight matrix of a factor in a given molecular layer. And again, thanks to sparsity priors on the weight matrix, this often gives a very clear picture where only a few number of molecular features, for example, genes, are important for this factor and seem to be the driving genes behind such variation we see in the data. And if a single gene does not tell us too much, we can also jointly aggregate information from multiple of the molecular features, for example, by conducting enrichment analysis of the weights to test for feature sets, such as, for example, gene sets that are linked to a certain factor. Now, I've showed you the basic principle that is behind multi-omics factor analysis and the R framework. And now I would like to show you 2 applications where we've applied this framework in order to dissect a complex biological system. And the first application is from the field of personalized medicine, where we try to understand the sources of patient-to-patient heterogeneity in blood cancer, or more specifically, chronic lymphocytic leukemia. So for this, we applied the method to 200 leukemia samples that were characterized by 4 molecular assays. We had genomic information on them, RNA sequencing, methylation areas, and ex vivo drug response assays telling us how the samples respond to certain drugs. And as you can see, not all of the patients were profiled completely. So for example, for the RNA data, we only had a subset of the patients, and that's a missing value structure that MOFA can handle. If we now look at the factor we get from this application, we can see that some factors, like for example, factor 1, is important for all of the molecular layers, while factor 4 is only important in one of them. And if we look into more details in the first factor, we can see that this actually nicely recovers an important clinical marker, which you can see on the bottom left here. So this distinguishes 2 clinical subgroups that are known for this disease, CLL, and is given by the genomic marker IGHV. But we can also link it back to other molecular layers and immediately tell what are the genes that are linked to this distinction between the subgroups in terms of gene expression, and which are the tracks that show differential responses between the patients depending on where they lie on the factor. And also we can use this to refine the clinical marker and also identify outliers like the red point on the bottom, where the biological background of the sample does not correspond well to the clinical label, which might actually be wrong or misleading. And last but not least, we of course also wanted to know whether the factors can be useful to predict the clinical outcome for a patient. And for this, we looked whether the MOFA factors are associated to the time to treatment and can provide an improved prediction compared to models relying on a single omic. And this is indeed the case. So we saw that 3 of the factors were significantly associated to the time until a patient needs treatment again. And by combining the MOFA factors in a predictive model, this actually did better than if we just used one of the molecular layers or if we just concatenated all of them in a naive manner without accounting for the structure. Now, in the second application, we made use of the group framework. So far, we only had one group of samples, but multiple molecular layers. In the second application, we now have a single molecular layer, but distinct groups of samples. So this is a study on single-cell RNA sequencing, where we had about 16,000 single cells from mouse embryo at 3 distinct developmental stages, from embryonic day 6.5 to 7.25. And we were interested in what are the molecular processes that underlie the developmental decision of a cell, so which direction or which tissue a cell will form when the embryo develops. And for this, we again applied MOFA to this data, now with groups of samples, as you can see on the bottom here, with 2 replicates at each developmental stage. And we can again see that some factors are important for all of the sample groups, while others gain more and more importance as the development progresses. So for example, factor 4, you can see is not active at an early developmental stage, but gets more and more active later on. And if we look into this factor, this actually very nicely captured the emergence of a specific cell type, the so-called mesoderm lineage, at the embryonic day 7. So that's the pink cells here. And these cells will later form your muscles and blood vessels and start to emerge at embryonic day 7. And if you look into the weights of this factor, we can see that this actually nicely links to proteins that start getting up or down regulated with the emergence of the cell type. So that brings me nearly to the end. I just want to quickly mention some related work and ongoing research in this area. So far I've showed you that with this framework of multi-omics factor analysis, we can encode group structures both among the features, such as, for example, in multi-omic data, as well as between the samples, such as, for example, with having different developmental stages. But of course, there are also other types of data structure that can be important, like, for example, for temporal or spatial data, where we have continuous structures among the samples, or if we have network information on the features of the samples. In addition, it might be interesting to look more into nonlinear extensions of the model. So far, we always had a linear mapping from a latent space to the observed data. And of course, strongly nonlinear patterns might be missed by such an approach. And then I quickly want to mention a related approach. So far, we've only looked into unsupervised integration of multimodal data, trying to infer latent factors in an unsupervised manner. However, sometimes we might also be interested in a supervised integration. For example, if we want to predict a certain response of interest, like, for example, clinical outcome, based on different molecular layers. And for this, we've also developed an R package called Craper that adaptively weights the different data modalities in such a regression framework in a data-driven manner and tries to give the best weight to each of the data modalities to predict the response of interest. And this already brings me to the summary of this approach. So I've shown you that with multi-omics factor analysis, we've implemented a Bayesian factor analysis model that disentangles the sources of variation in multi-few as well as multi-group data, or both. And it can cope with missing value. It's scalable to hundreds of thousands of samples or features, and it yields interpretable results by the use of sparsity priors. We've implemented the package so that it interfaces with many important or common classes, such as multi-assay experiment container for multi-omics data or the Seurat package. And for model training, we used Reticulate to interface our package with Python, which is a really nice approach to combine Python and R in a nice manner. And last but not least, we implemented various functions for downstream analysis in the package, as well as in the Shiny app, to allow users or researchers to upload the data on the trained model and explore them in an interactive manner. The software MOFA is available from Bioconductor, and the successor, which also has the multi-group framework, is still available from GitHub, and the Shiny app is on our EBI server. And then to conclude, I just want to thank everyone who was involved in this work, especially Ricard Agelaget, with whom I co-authored the package, as well as Oliver Stegler, Wolfgang Huber, Daniela Predikin, and Damian Arnold, as well as everyone else who was involved in this. And I also thank you a lot for your attention. And I hope that I see many of you later in the Q&A session.
Thank you very much, Britta, for the very interesting talk. And also on behalf of the whole organizing committee, I would like to thank you for taking time to prepare a presentation and to be present at e-Rum, even though virtually. Actually, for a pure coincidence, I am about to start a project that will involve multi-omic data. So I've had a look at the literature on MOFA, and I have to say it looks pretty promising, and I'm planning to give it a try in the near future. So if I have questions, I think I know now whom I can ask.
Yes, please contact me. I'm very happy for any feedback.
And yeah, so Britta, together with the other speakers, will be available at the end of this session for a round of Q&A, and I will give you instructions at the end of this session to let you know how you can join it. Thank you again, Britta.
Thanks. Bye.
Bye-bye. And now it's time for me to welcome on stage our second speaker, Emanuele Guidotti, who can join now us on stage. Actually, Emanuele is a special guest together with our next invited speaker. Hi, Emanuele.
Hi.
Good morning.
Good morning.
Because Emanuele is one of the two winners of our COVIDAR contest. What was COVIDAR? COVIDAR is a contest that we decided to organize as e-Rum 2020 when the pandemic broke out and we decided to go virtual with e-Rum. And the topic of this contest was all sorts of contributions that could be made with R to collect, gather, and analyze the data about the pandemic that just broke out at the beginning of the spring. Many of you have actually probably already met Emanuele and the next speaker, Mark Henley, during the pre-conference event that we held on May 29 that featured a lot of interesting talks, out of which we selected the two talks that will follow now in the program. Emanuele is a PhD student in finance at the University of Neuchâtel in Switzerland, and in his presentation, he's going to tell us more about the COVID-19 Data Hub. So without further ado, I'll give the word to Emanuele.
Okay, thank you very much for the introduction. It is a pleasure to give this talk today. My talk will be divided in two parts. First, I will give a general overview of the project of COVID-19 Data Hub, and then I will show how to import COVID-19 data directly in R. So let me share the screen. Okay. Okay. This is a joint work with David Ardia from HEC Montreal. So welcome to COVID-19 Data Hub. As you may know, the World Health Organization identified key open scientific questions to tackle the epidemic, including socioeconomic and behavioral risk factors, transmission dynamics of the virus, role of the environment, susceptibility of populations, effective policy measures. To answer such questions, no doubt COVID-19 data are immensely useful, but unfortunately, they are released by heterogeneous data sources in different languages in several formats, and are hardly accessible to the average researcher. The goal of COVID-19 Data Hub is to provide a unified, easy access to worldwide fine-grained data. How to do? We implemented an R package designed to aggregate the data from several sources. We put effort in making everything open source and easily extendable. We need native speakers to search for local official data, understand the data, and integrate the data in the package. We had people from India, Poland, Russia, Sweden, and more collaborating on GitHub. The package is exploited by a dedicated server which downloads the latest data and makes them available on a cloud storage on an hourly basis. These are CSV files that can be used by any client application. The files were downloaded 222,000 times in the latest 22 days. We implemented out-of-the-box clients to retrieve the files. First, the COVID-19 package on C-Run. This is not the GitHub package we use to aggregate the data. This is the C-Run package available to the end user to retrieve the data from our cloud storage. To respect the terms of use, we cannot store World Bank, Google, or Apple data. But we can provide additional arguments to download such data and extend our dataset in real time. We're now implementing a similar client for Python. We published a quick article on Towards Data Science where we show how to quickly build data-driven Shiny apps using our package. Simply connect the Shiny inputs to the COVID-19 arguments. The function uses an internal memory caching system so that the data are never downloaded twice. We do our best to guarantee the data quality and consistency. We keep track of each source for each data. We generate an error log that already spotted 3,000 misalignments in the official data. We rely on the open source community. Everything is open source, code and data. The bigger the community, the faster possible bugs will be notified and fixed. We also offer vintage data, daily snapshots of the data, so to ensure research reproducibility. Our dataset includes standard COVID-19 variables, policy measures by Oxford COVID-19 Government Response Tracker, geographic information to easily plot on a map for data visualization or merge with external databases. For example, weather information, geolocated tweets, etc. Finally, we provide external identifiers to easily extend the dataset with World Bank Open Data, Google, and Apple mobility reports. Governmental identifiers are also provided to further extend the dataset with local fine-grained statistics. For example, for Italy, Istat identifiers have been implemented. We support 194 countries, and more interestingly, we support 545 regions and 4,000 cities, but they correspond respectively to 19 and 6 countries. I would like to take the opportunity to ask you to join the mission, support new data sources, and improve the project. I would like to thank Hack Zurich for the support in the very early stage of the project, the Canadian Institute for Data Valorization that is funding the project, and all the volunteers who have joined us. In the few minutes left, I would like to show how to use the Data Hub in R. So let me change to RStudio. Okay, so first we install the COVID-19 package from C-Run, and we require the package. But the only function in the package is the COVID-19 function, which takes care of downloading the data. By default, the function downloads worldwide data by country. So let's have a look at the dataset. The dataset is a long table, including some data, and I will spend a couple of minutes in describing the dataset. So here we have an ID, which is the identifier of the location, the date of the observation, and here we can see the first block of variables, which are standard COVID-19 variables, such as the cumulative number of tests, confirmed cases, recovered, deaths, and hospitalized patients on date, requiring ventilation, and patients in intensive therapy. We also provide the population for the given location. Then we have a second block of variables, which are policy measures by Oxford COVID-19 government response tracker. This is a collection of policy measures that are being implemented all around the world to tackle the epidemic, such as the closing of schools or the workplaces, the cancellation of events, the restriction on gatherings, transportation closing, stay-home restrictions, and internal or international movement restrictions. We also have the information campaigns and the testing policy, which is adopted by the government, as well as the contact tracing. And all this information is putting together in a stringency index, which is an index by Oxford, which is measuring how strong the measures are to allow a cross-country comparison. Then we have a collection of country identifiers, such as the ISO code, which can be used to merge our dataset with external databases, and a collection of geographic information, such as the administrative area, the names of the administrative areas. So like the country names, here we have region or state names, which are NA now, because now we are considering country level data, and administrative area 3, which is usually city or municipality. We also provide the latitude and longitude to allow to extend the dataset with additional exogenous variables depending on the position, such as weather information, and which can be useful to study the virus. Also, we have additional identifiers which can be used to merge the dataset with, in this case, Apple data and Google data. Okay, we keep track of each source for each data. So how to access this information? We store the information together with the dataset. And here we have the data. Here we have the table for the data sources. So here we can see, for example, for Italy, you can see exactly all the data sources that are going to build the data set provided. So Italy, level 1, so national level data. The data type we are interested in, so let's say tests. And here we have the repository from which they are pulled, and they're pulled from Ministero della Salute, Italia. By default, we offer clean data. So we do a bit of pre-processing. This means that we download the raw data and we fill missing data with the with the previous non-missing data. This is suited for data visualization, but may not be suited for more advanced analysis, where you are more interested in the raw data containing missing values. This is achieved by setting the argument row equal to true. This will skip all pre-processing and will return you the raw data from official sources. So here we can see exactly the same data set as before, but with NA instead of zeros or instead of the previous value. Okay. Now we can also download state or regional level data by setting the level argument. This level argument controls the granularity of the data. By default, the COVID-19 function uses level 1, so national level data. Level 2 means state, regional level data, and level 3 is also supported, so that you can download city level data or municipality. So let's have a look. And again, you can see that the structure of the data set is exactly the same. What's changing is the granularity. So if we go here, we can see that now we don't have only United Kingdom, but we have administrative areas of level 2. So for China and many, many others. Level 3 is also supported. And also you can filter the data you're retrieving by country. So in this case, we are going to download Italian data for cities, city level Italian data. Again, the structure is always the same. And here you can see that each row corresponds now to a city. Let's have a look at Milano. Okay, Lombardia, Milano, and the latest data available as of today. You can see that the official government is not providing city-level data for deaths, but we are using data from Center of Excellence in Economics and Data Science from the University of Milano, where they are collecting data at city about death at city level via web scraping. So for some cities, we also have, like Firenze, we also have the number of deaths at city level. Okay, this is mainly, this is most about COVID-19 data, but we can extend the data set with additional databases, such as World Bank, for example, which is a very large repository of national level statistics, for example, GDP. So if you're interested in GDP statistics at national level, you can go World Bank, copy the World Bank code, and put the World Bank code here. This will download and extend our dataset with World Bank Open Data. In fact, here you can see GDP or the number of hospital beds. Also, you can extend the dataset manually by hand, since here we are offering also key identifiers at city level or state level. And these are usually governmental identifiers that allows you to merge this dataset with local fine-grained statistics. You can also extend the dataset with Google Mobility Reports. So you will see here there are change in the residential occupation, workplaces, transit, and the occupation of parks, grocery stores, and retails. And you can also extend the dataset with Apple Mobility Reports. Everything I showed is available in the COVID-19 documentation and in the examples below. Finally, we have the website where you can directly download the data in a CSV format together with the error logs and the vintage data. Here, it is available the documentation of the dataset that I quickly went through now. And what I explained is the R package API to the COVID-19 Data Hub. We also have a Python API and some instructions for other programming languages. If you're willing to contribute, don't hesitate to join us on GitHub and implement a new data sources. We implemented a quick tutorial to help you get started. And thank you so much for your attention. I hope you can find this dataset useful.
Well, thanks a lot, Emanuele.
Thank you.
Both for entering the competition of COVIDAR and for being here today to present. We really believe that the R community can give a great contribution in trying to understand the trends and the situation in the world around the current global pandemic. And what we really need really desperately is indeed a centralized place where we can access data and also, of course, good quality data. So we think that the work that people like you and many others are doing is very useful, and yeah, it's helping the world in a sense.
Thank you so much for your words. That's exactly the motivation behind the work.
All right. So thanks again.
Thank you.
So a little technical note, you may have heard earlier a little bell that chips in every now and then. And I've been told that I should actually warn you and explain you what it is. So it's just a signal for the speakers that tells them that they have 3 minutes left for their slot, for the slot allocated to their talk. So If you hear it, don't be scared. It's just a technical way that we devise to avoid interrupting the speakers. Now, I would like to welcome on stage our third speaker, Mark Henley. So, together with Emanuele, Mark is the other winner of the COVID contest that we held at the end of May. Hello, Mark.
Hey, Marco. Good to see you again. How are you?
I'm good. And you?
Yeah, good. Thanks. Good. Yeah, I wanted to say thank you so much to you all for having us here, to the organizers who have just done such a great job to adapt to this virtual conference. And I was just looking earlier at all the different international flags, and it's one of the real silver linings that we've all been able to come together like this.
Yeah, I think the real added value of this virtual conference that, to be honest, we had to rearrange in a blink of eye. We had a couple of months to basically reframe everything in a way that we try to keep as close as possible to the physical event that we should have held in Milan. Is that it has widened very much our reach, and now we really have people from all over the world that maybe wouldn't have been able to join us physically in Milan, but now instead they can be here. We also have really presenters from all over the world. As a matter of fact, you are in Oceania, if I'm correct.
Yes.
Am I?
That's right. You can see it's nighttime behind me.
You are really on the other side of the world. And we're very happy to have you here. So Mark is a lecturer at the Center for Big Data Research in Health of the University of New South Wales in Sydney. And today he will present us his work on the R package Covoid that is indeed one of the two winners of our COVID-R competition. So I'll leave you now the word to you, Mark. So please go ahead.
Awesome. Thanks, Marco. I'm just going to share my screen. And I hope you can see my slides now. And
yes, now we can see it perfect.
There we go. Now my video's off.
Yes.
Okay. So thanks for the opportunity to talk about Covoid. Covoid is joint work with my colleagues Oisin Fitzgerald and Tim Churches. Tim, Oisin and I live and work on Gadigal land. The Gadigal people of the Eora Nation are the traditional owners of the land. And as is customary here in Australia, we'd like to acknowledge and pay our respects to their elders, past, present, and emerging. And we particularly extend that respect to any Indigenous community members joining online today. We'd also like to thank Ian Sharp, philanthropic supporter of UNSW, and Ian's really generous work has facilitated our work on this project. Okay, so what is Covoid? Covoid stands for COVID-19 Open Source Infection Dynamics, and Covoid is an R package that provides users with a set of tools for modeling COVID-19 while incorporating time-varying interventions. So users can choose from 7 different epidemic models. They can specify flexible time-varying interventions and then go on to compare future projections under different scenarios. The package also includes a Shiny interface to help users quickly orientate themselves to the workflow. So kind of like Emmanuel, I'm going to have a 2-part talk where I present a little bit on slides, and then I'm going to demonstrate the workflow using the Shiny app. But before getting into it, I just want to talk about our motivation. So obviously, how our governments respond to this pandemic has really profound health and economic consequences. And because these decisions are so important, it's imperative that the underlying models and the assumptions are explicit, and that those assumptions really should be transparent and open for us to debate. Ideally as well, the model should be open source and reproducible so that other research groups can replicate and interrogate results. Now, As you guys will all have seen, highly influential modelling from Imperial College London has informed policy in the UK and internationally. Here in Australia, the pandemic response was informed by similar epidemic modelling. But in both cases, the authors were slow to release the modelling code, particularly in the case of the Imperial College Code. It was heavily criticised, described here as a 15,000-line file that had been worked on for a decade. So obviously not the best practice for reproducibility. And our project really started out as an effort to implement similar models in a way that would be transparent, open source, and reproducible. And with these goals in mind, the R language was a natural platform for our work. And very early on, we decided we would try and release our work as an open source OR package. So I'll talk you through some of the features of the package. Currently, Covoid allows users to choose from 7 different variations of the standard SI or compartmental model. You may be familiar with this type of model, but if not, a brief explanation is that everybody in the population is assumed to belong to one of these compartments. In the most simple case, the compartments are susceptible, infectious, and recovered. Assumptions we make about the disease pathology, for example, the OR0, the basic reproduction number, define a series of ordinary differential equations that govern the rate of movement between these compartments over time. Now, we can use out-of-the-box tools to solve these equations, and that gives us the number of people in each compartment over the course of the pandemic. The simplest models implemented in the Covoid package are like this. So they're the 3-compartment SIOR models, but there are much more nuanced models that incorporate additional compartments to better reflect reality, such as for people who have been tested, quarantined, and hospitalized, and so on. Next, I'll just show you some really basic syntax for how to implement the simplest SIOR model. Just to give you an idea of the minimal set of parameters you need to run one of these. So first of all, you start with the model parameters. In the case of this really simple model, it's just 2 parameters. So OR0, the reproduction number, and gamma, the recovery rate. And the second thing you have to define is the set of initial conditions. And that's the number of people in each compartment at day 0 for your model. You can then pass these 2 lists to the simulate function. There are many different flavors of this simulate function corresponding to the many different variations of this model that are implemented. And that's it. Once you run this, you can then plot the results, and you get something that looks like these epidemic curves that you'll have seen a lot of lately, which show basically the number in each compartment over time. And the underlying data is also passed to the user if the user wants to further process that. So that's a very basic implementation. Now I'm going to talk about some of the features that make our more sophisticated models interesting. First of all, these are age-structured models. Now, because age is a key determinant of disease transmission and prognosis, several of the models account for population age distribution, as well as the estimated social contacts between age groups at a country level. And the package has built-in functions that allow users to quickly source this information. And that's available for over 150 countries, and it's all shipped with the package. I'll give you a little example of that. So this is using the helper function import age distribution for the country, for Italy here. And all of this data is UN data. It's coming from the World Population Prospects. But these functions allow you to quickly access it. By way of comparison, here's the age distribution for Ireland. So Italy and Ireland. You can see Ireland has a much younger age distribution. Italy is older, and you can imagine how that's very relevant, particularly with respect to COVID-19, that particularly affects the elderly. Okay, so as well as age distribution, the models can also account for the average number of daily social contacts between age groups. These contact matrices are sourced from the Polymod study, and this here is an example of using the helper function import contact matrix to get the the social contacts matrix for Italy. So as you can see, contacts are highest between same age groups, so you get that diagonal, and highest contacts for the teens and 20s, unsurprisingly. And again, just by way of comparison, here's the same matrix for Ireland. It's a little bit subtle if you're just looking over the screen, but if you interrogate this, what you can see is that Ireland has much lower social contacts, especially between different age groups. Next, I'm going to talk about another standout feature, and that's the ability to specify flexible time-varying interventions. Now, during the early stages of the pandemic, these type of compartmental models were used to support policies to flatten the curve. However, once the curve is flattened, the question becomes, how soon can we reemerge, and under what conditions? So to help address these questions, the models implemented in Covoid allow the user to specify flexible time-varying interventions. Interventions can target two facets of infection dynamics that can be influenced by policy. The first is the number of daily contacts. So that emulates things like working from home, social distancing. The second thing that's amenable to intervention is the probability of transmission. And that emulates things like wearing masks, washing your hands, and other good hygiene practices like that. So the user can specify these flexible interventions just as a vector in any flexible way, or they can use the helper functions. And this is an example of one of those functions, the contact intervention. And this specifies an intervention that would reduce the number of contacts by half, but does so in a way that it takes about 20 days for that measure to be fully implemented in the population. Now, all of this functionality is available in the downloadable package, but there's also a Shiny interface available that you can call from within the package, or is also available online on our Shiny Apps Hub. The interface is a good way to get started and get an idea of what's available in the package and the workflow, especially for non-coders. So I want to use my last few minutes just to demonstrate some of the workflow with the Shiny app. And here we have it. I hope now you're seeing my Shiny app. There's a lot of things going on here, so I'm going to just highlight some of the more important things. First of all, down the left-hand side, you've got a variety of areas that correspond to the workflow for this package. And we're in the area particularly for parameterizing the model. And here you can do things like choose the country and age distribution. You can specify the initial conditions, so how many people in each compartment on day 0. And you can specify the model parameters. So for example, the reproduction number. That's all I'll say about that for now. I'm just going to go ahead and run a simulation based on these default parameters. Now, once again, there's a lot going on the screen, so I'll just draw your attention to the lower plot here. And we've got a plot with 2 lines. This is showing incidence. The blue line is the model estimated incidence, and the gray line is the actual observed incidence over the last few months in Italy. And as you can see, the model is doing pretty well over the first few weeks, but then it kind of goes into this realm that is outside of reality. And the reason for that is because the model at this point is not taking into account any of the interventions that actually happened in Italy throughout late February, March, and April. So the next thing we're going to do is go ahead and define interventions. And the first intervention I'm going to define are exactly those interventions that have happened. So we can do that in this screen. And this is a little point-and-click tool that allows you to specify flexible interventions. This pink bar represents what would happen if we had no intervention. But I'm gonna use the tool to illustrate what happened in Italy. And we know that in Italy, the lockdowns started in February, quite slowly initially with the Lombardy region. And I'm just representing that by clicking dates and points. You can do this more exactly when you have more time. And we know that it increased over the course of March to the point that by the end of March, there was a very stringent lockdown in Italy. And having specified that intervention, we can now run the simulation again. And we can watch our little undulating covoid. And now we can see we're getting something a bit closer to what actually happened. I'm going to stretch out the timescale there a bit. Okay, so now our blue line, which is the model prediction, is looking a lot closer, not perfect, but better to what actually happened. So I'm going to save that result. And this is the kind of recommended workflow, is that we're first calibrating to what actually happened, but now we want to go out and see how the future looks. So we can extend the time frame here. With the intervention I specified, I assumed that that intervention would stay in place in Italy for the rest of the year. Of course, that's not going to happen. So now we can start thinking about what's going to happen next. And this is the real power of the app, that you can start specifying different interventions and see what happens. So I might specify that we'll continue in lockdown until July, but then gradually reemerge such that things are back to normal perhaps by the middle of October. And it's very quick and easy to do with the point and click tool. Now let's update our simulation. And no prizes for what's going to happen here. I've said we're all going to go back to normal. We're going to be back eating ice cream and visiting our grandparents. And when the model converges or their simulation finishes running, what you see is that we're going to get this second spike. So you can do much more finessed interventions and explores what happens under different scenarios. The final thing I'll do with my final minute is just to flag the report canvas. As I've been creating these different models, anything that you see on screen here, I can save to the report canvas using this little feature. And then you can come to your report from canvas and revisit the models. You can look back at what you've done, and you can make comments about the different interventions that were implemented. And then when you click download report, that will knit it together and just give you a quick knitter report that summarizes the different interventions you've explored and the outputs under those interventions. So that's a quick demonstration of our Covoid Shiny app. So I'll stop sharing the screen now and turn on my video again. So thanks so much for your attention. Tim, Oisin, and I are all going to be available in the Q&A later. So please do jump in and let us know if you have any questions.
All right. Thank you so much, Mark. And congratulations actually for winning Covoid with the impressive work that you have been doing. I actually see now that we have almost 700 people who are following now online. So it's definitely more than probably the capacity we would have had at the physical event in Milan. So quite impressive, I have to say.
That's amazing.
Yeah, okay. Thanks again. And now I would like to welcome on stage our next speaker, Edwin Thun. I would like also to say that I'm seeing that a lot of you are actually tweeting about e-Rum and also expressing their appreciation for how the event is going so far. And we're really happy to hear your positive feedback, and keep on tweeting. Hi, Edwin.
Hi, Mirko.
So actually, by pure coincidence, that's the second coincidence of this session. Edwin and I have never met, but we happen to be in the very same city. So this is really the power of e-Rum. It's bringing together people from the world, but also people that happen to be in the very same city.
Yeah.
So
I guess it's my fault because I fled academia.
So basically in the beautiful city of Leiden in the Netherlands.
Yes.
So Edwin will be our last speaker for the session, after which we will have a Q&A. And Edwin works as data scientist at the Dutch housing site Funda. And today he will be talking about how to build data science products in an agile way using R. So please, Edwin, the floor is yours.
Thank you very much, Mirko. Then I'm going to I'm not seeing my presentation as of now, so maybe if I...
Yes, I can confirm that it's not yet been.
No, I cannot see it with my. Let me. That is a pity.
Yeah.
Let me really quick try to find a workaround.
Yeah, so while we fixed it, for those watching, Hopin is actually a great tool, but it comes with some technical
yeah,
things
I
that
have
we
this
need
with
to
other
manage.
things too.
Okay.
And if I go to play mode, is this all right?
I can see, yes, that's
Yeah.
working perfectly.
And if
so
I go to the next slide, is this working?
Yes, that's perfect.
Okay.
Indeed. Thank you.
And then I need to hide myself, right?
Yeah.
So
Great.
I will do that right away. Okay.
Thanks.
Sorry.
Yes.
Sorry for this quick.
No worries.
Delay.
It's the first time for everyone today on Opin, so.
All right. Yeah, I think it's due to preview on Mac. So for the further speakers, please be aware. Okay. I'd like to start with a recipe for disaster. And we take the following ingredients. You need one statistics master of science with no software engineering skills. You need a consulting firm, one customer side, a bunch of project stakeholders, one ill-defined project, a handful of undocumented databases. So with the ingredients, you do the following. The preparations are use a consulting firm to sell the statistics masters at an experienced data scientist, place the data scientist at the customer side, have the stakeholders convincingly explain the project and set a deadline in the far future. Be sure the data scientist starts trying a great number of models and algorithms, let gradually simmer for a couple of months, and as soon as the project implodes, you know it is done. And this is, of course, not a randomly chosen description of a data science project. This is how I started my own career. This is unfortunate, but I think many practitioners in commerce, but maybe also in other applications, can relate to this. In spite of all the goodwill that we show and all the hard work that we put in, our projects often change very little in the company or organization we work in. And we probably have no trouble finding promising relationships, but somehow we seem unable to have these results being implemented. So a quick browse on the web learns that an estimated failure rate of data science projects is about 85%. I will quickly introduce myself before I go on, because I also think it is fundamental for the rest of the talk that you know what I'm working on typically. So as Mirko introduced me, I'm a data scientist at the Dutch housing site Finza. And I have now about 6-7 years applied experience. So these descriptions at the introduction, that was at the very beginning of my career. Hopefully I've learned a bit in that in the time being. And I mainly focuses on large machine learning projects. So that's what I will be relating to mostly. So just that you know. And also I do some quick research. In software design, there too is a problem of projects that do not really fulfill their promise. A methodology called waterfall was the norm for decades, and it prescribed that a product should be completely finished before it could make it to production. This caused long durations of software development, with projects sometimes running for over a decade, and it led ultimately to a lot of failed projects. So in 2001, this group of handsome young men came together in a hotel in Utah and drew up the Agile Manifesto. And the manifesto contains 4 philosophical core values and 12 more practical applicable principles. And in this talk, of course, we're not going into detail of all those practical, of all those principles and all those values. That will not be feasible in just 15 minutes. But if you'd like to learn more about them, then you can read the text that I created here. It's my view on Agile data science. And yeah, it's pretty lengthy. So if you've got the time, please visit this link and you will find a what I call booklet. So it's somewhere between an essay and a book, in which I treat all kinds of aspects of what I think is Agile data science. But for this occasion, let me jump to what I see as the essence of data science. And that is, don't wait with bringing your product to production until you think it's totally ready. It can take many months or even years before this happens, if this happens at all. You probably never think you're completely ready. Rather, as soon as your product is just good enough to deliver some value, productionize it and let the user or the customer interact with it. From these interactions, you can learn what the next best step is and improve to that. I think there is a close analogy to what David Robinson advocates for with respect to making work public. So this is an excerpt from his keynote at our StudioConf about a year and a half ago. And he argues that as long as the work resides on your system only, and it's not brought into the open, it's basically invaluable. And I think the same holds for work within your organization. If it's on your machine only and no one else can access it, you really not have contributed anything. So delivering early might push your panic button. You don't feel ready because, well, you're not really ready. Your reactions might be one of the following, like my R² is only 0.39, or I still have 6 more tabs in my Shiny to make, or my third data source is not connected, or my AUC is not there. What it all boils down to is that you don't want to deliver a low quality product because you're a high achieving, concise data scientist or whatever you call yourself. And I think this is one of the main misconceptions about Agile, is that you deliver early means that you create something of low quality. So if you see the gray box as the ideal product and let's say the area of the box is the time that you spent on the product, then you want to have a product that is both complete and that is of high quality. So as we advocate for productionizing early in what we call a minimal viable product or an MVP, then many people think that it looks something like this. So that's a product that has already many features, but that we cutting corners on quality. So this is what I call a fingers crossed push to production. But rather what your deliveries should look like is this. Only a part of the envisioned product features is implemented, but you don't cut corners on quality. From what I've done and seen in the past, a pitfall for data science work is that we are in explore mode for many months until we think we're ready, and then not really taking care of quality while we're doing all this research. I personally think one of the best things you can do to write high quality software is to do so from the start of the project. So now exactly what are the advantages of delivering early? Why do we want to do that in the first place? Well, first of all, you keep the excitement around your product alive. Often a project is started with the firm belief that it's going to be a game changer for the organization, but then it gradually bleeds out because you as a data scientist might report on the progress, such as AUC or R², or whatever statistic you choose to report on. But in the eyes of the stakeholders, there's nothing happening. And they're actually right. So delivering working software, even when it's far from complete, is much better than just doing all kinds of status updates or status emails or meetings or whatever. So the second thing is that you find out quickly if you're solving the right problem. Let me give a little example here. So say you work for a telco and you want to do churn prediction. So you want to pinpoint which customers are likely to cancel their subscription. So you agree with your manager or another business stakeholder that you will assign probabilities to customers that indicate how likely they are to churn within a month. And then you build an MVP from this within 1 or 2 months with a very simple model. So you just fit a simple GLM, and it's not perfect, but at least we have some kind of value in that we can distinguish the customers that are more likely to churn. Now, you deliver that data set to one of the customer success employees who follows up on the customers, and she discovers that they actually already canceled, or that they are so likely to cancel that she cannot do any interventions anymore. So all this time, you would have been optimizing the wrong problem if you didn't build the MVP. So now you can quickly adjust to this and predict it in a longer time span. And the third advantage is what I call that you avoid weaving a web of complexity. So the longer you work on a project, typically the more complex it becomes. And it's my own experience that when you keep researching for too long, you can create a massive project that contains many scripts, and it's very difficult to disentangle the actual product that should be productionized once you're ready. So the earlier your aim for production, the lower the risk of doing this is. So I hope that I've convinced you a little bit of why it's important to build an MVP and not wait too long with productionizing, even though you don't feel you're ready. Now I'd like to talk a little bit of what is so challenging for data science. This is that other than software development, we have to deal with the uncertainty of yet to be discovered data relationships. So building a data science product requires a lot of research on top of the software development. So where software development is quite clear in what the expectations and the requirements for the product are, in data science, we cannot just outline upfront what we're going to build. And what for me works very well is a two-world workflow. And now you see two faces. I probably assume that most of you recognize the face on the left, which is Marie Kondo, the Japanese tidying up guru. On the right-hand side, you see the Austrian philosopher of science. And I'm gonna explain to you what they stand for. So Mary is the software world, where everything is ordered, structured, and serene, and where everything is right on its place. And the motto of Paul Feyerabend was anything goes as valid science, and he published the book Against Method. And I also think his face is just the perfect representative of chaos and anarchy. So he represents the research we do. In Mary's world, we developed a product. It should be well organized. Ideally using the best practices such as documentation, unit testing, writing clear and maintainable code. And of course, this is also where complete reproducibility should be attained, because after all, this is the code that we're going to productionize. Now, in the research world, it's all about speed. You don't want to test hypotheses by adjusting the product code right away. It will take too much time, and if the results are not what you want or what you have thought of, then you have to revert everything, and that slows you down and can get really messy, something that we don't want to happen in Mary's world. So rather we test the outside the product and only adjust the product code if it appears that the research that we did really had the envisioned effect on the product and improves it. So research cycles should be short, and it's okay if they're quick and dirty, and even low reproducibility is quite okay here. Now, you might think we're already at 3/3 of this talk and you have not mentioned R once. This is an R conference. Well, I'm really sorry that I took all this time to introduce myself, but the good news is that I think the R package structure is ideal for the dual mode of working. Of course, an R package is the way to create a software product within R. It allows for documentation, testing, and versioning, and all other best practices. And personally, this is not, of course, intrinsic part of an R package, but I love Drake that I use to link all the functions that are created within the R package, and to create like this sequential flow from this. So when it comes to software development, R packages spark a lot of joy. Now, what about our grumpy philosopher? What does R have in store for him? And the answer is R Markdown. You can create a dedicated folder with research scripts within the package or outside it, whatever you prefer. And the big advantage is that if you keep your entire product as a package, all the functions that are created within it are at your disposal at all time in your research as well. So you don't have to source scripts or make sure they are loaded into memory in some like non-reproducible way. So I use DevTools Load-All for this, but there is, of course, other ways you can even pack up the package and load it using library. And you can use these Markdown files to quickly come to conclusions. These are outside of your software product, but they can make use of the things you do in your software product anyway. So it's about time for me to wrap up. I'd like to highlight these 3 parts of my talk. We discussed that delivering early and then update continuously can lower the risk of failure to a data science project. We also discussed that it can be very beneficial to mentally and physically separate doing data science research from building a data science product. And finally, I hope that I convinced you that using the R package structure has the ingredients to create data science products in a very agile way. So thank you very much for attending this talk, wherever you are. A huge, huge thanks to the organizing committee, not only for inviting me, but also for the perseverance you show by organizing still this conference in whatever the way it could be held, even though your own region of Lombardy is hit so brutally with the COVID-19. I, of course, will also be in a Q&A session after this. And if you would like to confirm with me outside the conference, this is my Twitter hashtag. I also sometimes tweet about Agile data science. Well, not sometimes, quite often. And once again, below is the link to the resource.
All right, back we are. So, well, thanks, Edwin. I think we can fairly say that your presentation really sparked joy.
Thank you.
So I have now a few things to say before we move on to the Q&A session, a few reminders. And actually, before doing that, I would like to thank again all the speakers, Britta, Emanuele, Mark, and Edwin. And there's also 4 persons that I would like to thank specially. Because, of course, there's an organizing committee behind this conference that has involved several people. You can find all of their name on our website. But inside e-Rum, I've been taking care especially of one part, which is the management of the team that coordinated promotion and social media. And I could never have done this without the help of 4 persons. And these persons are Gert Jansen-Willen. Dutch is difficult, Edwin, as you may know.
I find it quite easy.
Yeah, fair enough. Serena Signorelli, Andrea Guzzo, and our graphic designer, Vittoria Toso. So please, guys, join me in thanking them for all the amazing work they did in these months to help us managing the communication of e-Rum, even when everything changed all of a sudden. Another reminder is that if you missed some of the talks or you would like to rewatch them because, well, maybe you were doing something else or you were not focused or you missed something, you can find them on our YouTube channel, which you can reach from the header in our website. And now it's time for the Q&A session, which will be open up until 11:10. And how does it work? The idea is that you can go to the left tab in Opin and click on the sessions. And there you will find 4 rooms, each of which will be associated with the name of a speaker. So you can join these dedicated rooms where you will find the speakers, and there you will be able to ask your questions and to interact with the speakers. Don't be shy. You can also share your video and audio in these rooms because they work a bit differently from the stage. And yeah, go there and really please engage with the speakers who have really spent time and effort to prepare our talks for today. So I would like to close this session thanking again Britta, Emanuele, Mark, and Edwin. And now we can close this plenary session and move to the session area for the Q&A. Thank you all.
Hello, everyone. Welcome to this first keynote of e-Rum 2020. So I'm really happy to have on stage today our first keynote speaker, and she is Stephanie X. Stephanie X, she is an assistant professor at the Department of Biostatistics at Johns Hopkins Bloomberg School of Public Health. Welcome, Stephanie.
Well, hi, thank you. So excited to be here.
That's great to have you here.
First of all, just making sure.
Yes,
Okay.
I was just presenting you, and I mean, saying that you're an assistant professor at Johns Hopkins and a faculty member also at Johns Hopkins Data Science Lab, also a very active in the social stream of our co-host of the Corresponding Author podcast, co-founder of Our Ladies Baltimore, and also very active in the bioconductor community, if I'm not wrong.
That is all correct, yes.
Great, that's great to have you here. And she's here today. Today's talk, Stephanie Keynotes, is about something very important, using R and data science to improve human health. So I'm really eager to see and to listen to your words. Just a little reminder to our audience that we can also use this system, Slido. So join at slido.com with the code e-Rum2020 and ask questions. You can ask questions there while the talk is going on, and also upvote others people's questions. So we will have a Q&A session just right after the talk. Okay, so thank you, Stephanie, for being here, and I leave you the floor for your talk.
Okay, see if I remember how to do this. And okay, are you looking at my slides?
Yes.
Okay, and let me turn off my camera. All right, does everything seem okay?
Everything is good.
Okay, perfect. All right, well, hello everybody and welcome. I'm really excited to be here. I just wanted to say thank you so much to the program committee for the opportunity to present on how I use R in the life sciences. So I just will mention that my slides are available at the link below. Okay, so when I received the invitation to come give a talk today, one of the things I immediately thought about was the Milan Cathedral and being able to visit it. I've read about it in books and I've read about it online, and I was really, really excited to come see it in person. And the world that we live in did not let that happen today. So we live in a world, as we all know, as we heard about this morning from the Covoid art contest, that coronavirus hit. And in particular, Italy, for example, was one of the hardest hit regions or countries outside of China in February and March, with over 600 cases in February, rising up to 15,000 in March. But with this tragedy came a new opportunity, for example, as I mentioned, to host this Covoid R contest, where this contest was designed to develop open source R products like Shiny apps to explore data around the pandemic. I actually watched the whole event this weekend as I was preparing for this keynote, and I really enjoyed seeing all 15 of the presentations. And I just wanted to say congratulations to the winners and the awardees at the conference. Well done, well done. But as I was watching this, one thing that popped in my mind is I'm curious, like, what is the motivation that these developers and other developers around the world for creating these R resources around the pandemic? And so, as any good researcher does, I turned to Twitter over the weekend to ask, for example, for those who've downloaded, explored, or analyzed any COVID-19 data, looking at plots, web apps, dashboards, papers, what was your motivation? So a couple of ideas that popped in my head was maybe an individual wanted to help make an informed decision for an individual, a business, a city, or a country. Or maybe you wanted to just help a loved one, or maybe help humanity, or maybe it's just pure curiosity. And so this was interesting poll response. A lot of people seem to be just really curious. And then there were some comments that were left, such as maybe for academic research, a hackathon or competition, job for government agencies such as Ministry of Health, programming, visualization portfolio, or an exercise for a data science course. That made a lot of sense to me. Another one that I read was, I gathered some references, methods, and tools to assess when the local healthcare system would collapse. And when I read that, it got me thinking about healthcare systems and in general, and how we, as the world, are trying to overcome this pandemic. So I think one of the biggest ways that we are trying to overcome this pandemic, in addition to like social distancing, is to create vaccines, to produce an immune response in our own bodies whenever we encounter the coronavirus. To date, there are over 150 vaccines of SARS-CoV in various stages, with the first trial starting, I think, in March 2020. Now, as we all know, it typically takes years to research and test vaccines before they reach the clinic, but there are some scientists who are trying very hard to reach a safe and effective vaccine by early 2020. So I thought this was a great motivation to be able to introduce a little bit of biology. And so to do that, I thought, well, let's talk a little bit more about vaccines. How do you even create a vaccine? Well, it turns out there are many different ways to create a vaccine. For example, you could have a genetic vaccine, and this is a vaccine that where you use one or more of the own coronavirus's genes to provoke an immune response in our body. So the virus is introduced into our bodies, and the goal is for our body to produce an immune response to attack it. As opposed to a genetic vaccine, you could have a protein-based vaccine. So here you're using a coronavirus protein or a protein fragment to promote an immune response. You could also use a viral vector. So here you're using a virus to deliver the coronavirus genes into the cells. Or you could actually use the whole virus itself, just a weakened or an inactivated version of it. Now, as clinical phase 2 trials start to emerge, what will happen is we may start to see how different subportions of the population, for example, children versus elderly, might respond differently to vaccines. And you might ask, well, why is that? Well, to do that, we need to talk a little bit about biology. So I'm going to use this COVID-19 example as a motivation to talk about biology at a whole, and I'm going to switch from the concept about COVID vaccines to a broader question about what makes us diverse as individuals in a human population, because this is essentially what will drive how we end up responding differently to these vaccines. So if you recall, in my high school biology class or your high school biology class, for example, this story, to answer this question about what makes us diverse, the story starts with what's known as the central dogma of biology. So at the top here, we have a piece of DNA. Can you see my mouse by chance? I can't tell. I'm going to assume no. So we have a single piece of DNA here at the top. This DNA, or portions of that DNA, get converted into what's called RNA. It's also, you can think about it as a gene. That process goes through something called transcription. And then an RNA gets converted into something called proteins via translation. And so I've mentioned a little bit about these words when I was referring to the different types of vaccines. So whether you're using a coronavirus protein or a coronavirus gene, such as it in the DNA or in the RNA. Now, genetics is interested in looking at changes in the DNA and, of course, associating it with some phenotype. So they're interested in identifying if there's a small change in a base of my DNA, how does that change in the phenotype that I observe? So I'm going to pick on my colleague, Jeff Leake, for just a minute. Here are two pictures of species with different genomes, and they have two different phenotypes. And if you know anything about Jeff Leake, you know he's the exact opposite of a sloth, so this was a good analogy. Now, if we go back to the central dogma of biology, genomics is interested in how all of these things interact. For example, we're interested in looking at changes in the RNA or changes in the DNA, or how protein interacts with the DNA. So protein can go sit back on the DNA and cause it, for example, to go through additional transcription to create more RNA, which will then create more protein and so forth. And of course, associating all of these changes with some kind of phenotype. So let's talk about how genomic data is generated. So to answer that question, I'm going to start back at a piece of DNA. DNA, what we do with it is we fragment it up. We tear it up into tiny little pieces, and then it goes through an experimental protocol to produce what are called sequencing reads or reads. And they are essentially little short fragments of 50 base pairs or 100 base pairs or 200 base pairs or even longer that we use as the output from our sequencing experiment. So this is the output that we start with, these raw reads from the sequencing experiment. Now, turns out each biological experiment can have files with millions or billions of reads. And you could ask, what do we do with these reads? Well, the first thing we have to do is we have to figure out where these reads come from. So if we have some kind of reference genome, like a human healthy reference genome, we could use that to figure out where these reads are coming from. So that's exactly what we do. We start with a piece of reference DNA, and on it sits a gene, for example, so gene XYZ. What we get out of a sequencing experiment are a set of reads. And the goal is to try and figure out where these reads come from. So what happens is we compare the similarity of the A's, the T's, the C's, and the G's from the reads to the A's, the T's, the C's, the G's from the reference genome. And then what we do is, once we're confident about where they come from, we essentially count them. We say how many reads are coming from gene XYZ. And in this case, if I did my math correctly, there are 23 reads coming from gene XYZ in this one sample. So what do we do with that number? We put it in a matrix. So we start by recording these 23 reads that are coming from gene 1 in sample 1. And then we can repeat this for counting the number of reads that come from gene 1 and more samples, however many samples we have. And here it's 6 samples. Then we can repeat this process so we can count the number of reads that come from gene 2 in sample 1, 2, 3 through 6. And we can repeat this process up until we have gene G, which is usually around 20,000. We have around 20,000, for example, protein coding genes in the human body. So this is the matrix that most people are maybe familiar with if you've ever worked with genomic data, but I just want to point out there's also another piece of information. You can think about this as metadata that's also really important. It's essentially very important bookkeeping. It's information about where the gene comes from. So does the gene 1 come from chromosome 1? And what is the position that the gene starts, and what is the position that the gene ends on? I'm going to talk more about this metadata in a few minutes and how Bioconductor handles it. But in general, this is the type of data that we analyze. And this data can be data that's stored in a CSV file, or it could be data that's stored in a database somewhere and we're bringing it in, or streaming it in, or it could be data that are stored completely on disk, such as an HDFI file. It doesn't really matter. This is just a matrix of counts that we're typically working with. And we can ask interesting questions like, what is the average expression of gene 1 in samples 1, 2, 3, and compare that to the average expression in gene 1 in samples 4, 5, and 6. And a way we could ask for if there's a difference in the average expression between these two groups is something like a t-test, for example. All right, so how can we actually analyze this genomic data? I've now given you a sense of what are genomic data and how do we, what might we be interested in doing with it? Well, the way that I work with it is Bioconductor. So if you've never heard of Bioconductor, you can think of Bioconductor kind of like as a cousin to the CRAN project, but specific for the analysis of biological data. So formally, Bioconductor is an open source and open development software project for computational biology. Open source meaning anybody can read and modify the underlying code. Open development meaning anybody can contribute to the project. This began in 2001 by Robert Gentleman and others, and now Bioconductor actually includes 12 full-time core developers to build and maintain the core infrastructure. I think it has over 1,900 packages to date, so it's quite a big task to try and coordinate. But some big priorities for the project. They're really focused around reproducible research, addressing domain-specific challenges with high-quality documentation. So some examples. For example, each software package must contain a vignette. There is a huge community support forum that you can ask questions on problems and get answered by experts in the field. Bioconductor has a Slack workspace that's open to anyone. Many workflows to help users get started in analyzing biological data. Lots and lots of great teaching resources. And something that I really like is that Bioconductor strongly encourages the use of existing data and software infrastructure from Bioconductor packages to really enable interoperability. So there are a lot of great things about Bioconductor. And I think the mental image that I want anybody watching this to walk away with is that Bioconductor aims, I guess the mental image that Bioconductor is aiming for is that there are a lot of tools and packages for the analysis of genomic data, similar to the way there are a lot of individual musicians in an orchestra. And to make them all work together, Bioconductor functions as a conductor of the orchestra. It provides a flexible platform to integrate everything together. All right, so let's talk about a little bit what's in Bioconductor. So to do that, I thought I would showcase or highlight a package that I discovered in the last year or two called the BioC package tools. And here I'm showing you how in one line of code, you can get a tibble or a tidy data frame of all the download statistics for Bioconductor packages. So for example, in row 1, you can get the number of downloads for the package AB array from January 2020, and there were 117 downloads. I will mention there's a column called software here, or the repo here with with software in it. Software is the biggest type of package that's contributed to Bioconductor, but there are actually different types of packages. So we could figure that out really easily. And because this is a tibble or a tidy data frame, you can leverage the tidyverse essentially to explore it. So I can take the package's tidy data frame and I can filter it for all the packages from 2020. And I can essentially group by repo and count. So you can see that, yes, software is by far the largest set of packages in Bioconductor, but there are also these things called annotation data or experiment data. Annotation data really streamlines this tedious bookkeeping that I mentioned earlier. So depending on what reference genome you're using, the location of a gene might change. And it's really important to have infrastructure to make that as easy as possible. And Bioconductor has really done that well with annotation packages. Experiment data packages, they contain process data, and they're also really useful for teaching. So if you want to demonstrate the use of a package or use of a function in your package, you can use experiment data to do so. So Bioconductor software packages have really been steadily increasing over time, all the way up through 2020. It's really quite nice. And yeah, I think there's around 1,900 or 2,000 packages to date. So what is this standard, or like what are the different types of standard data infrastructure in Bioconductor? So I think the one to start with is a genomic ranges or a G ranges object. And here I'm representing a chromosome, chromosome 1, and I'm showing you two different genomic regions from this chromosome. So on the left side, there are 4 columns, and on the right side of this object, there are 2 columns. On the left side, these are required by a G ranges object or genomic ranges object. And on the left side, you can put kind of whatever you want there. That's it's however you want to, whatever information you wanted to keep track of about each genomic region. But on the left side, you have the seq name column, which contains information about what chromosome the genomic region comes from, the start and the end position. I'm going to ignore the strand information. That's a little bit too nuanced for this talk. And then I've incorporated a gene ID or gene name and some score. And you can think about the score, for example, as the number of reads that map to a particular genomic region. It can be really anything. So to create a G-ranges object, it's actually really easy to do. There's a package called Genomic Ranges, and in a few lines of code, you can have an object that Bioconductor expects to use in almost all of its packages. So it's really quite fun. So here I've got 2 genomic ranges similar to what I was showing you before. Things you can do with it, you can ask, for example, the width of the regions, or you could use base R syntax to filter rows and ask for rows that have a score greater than 15. I will give a shout out to the Ply Ranges package from Stuart Lee, Di Cook, and Michael Lawrence. They've developed a really nice API to be able to make genomic data analysis more human readable by being able to integrate the pipe from the migrator package and really extending the dplyr package with action verbs such as filter and subset or select and things like that. So shout out to them for being able to make it a more human or genomic data analysis more human readable, but I'm going to skip over that for now. Okay, so let's talk a little bit about one type of genomic data that I work with, and this is gene expression data or RNA. So the traditional way that people have measured gene expression is something called bulk RNA sequencing. And so for a given gene, you can see what you get is the average expression across all the cells in a tissue. So if I take a piece of tissue from the brain, for example, I can get on average how much RNA was expressed from a particular gene given all the cells in that tissue. You don't actually get to know what are the different cells that are present. An analogy that I like to use is Legos. So it's like you have a big pile of Legos, and for a given feature, such as the width of a Lego, you get to see an average of the widths across all the Legos in a pile. Now, turns out there are newer technologies, such as something called single-cell gene expression or single-cell RNA sequencing, and it's an advancement in the field because now we can capture all 20,000 features or genes in an individual cell. So we get information, new information about what genes are being expressed in each cell as opposed to an average across all the cells in a tissue. And it's really, really exciting because you can isolate these cells and you can use the cell profiles to do things like unsupervised clustering and group different cell types together and figure out if there are any novel cell types. An analogy that you could think about is with Legos is being able to separate the Legos and group them by size, color, and type. So using unsupervised methods, unsupervised clustering methods, for example, to figure out what are the different cell types in my big pile of Legos. So just a little bit more formally, single-cell RNA sequencing starts with a tissue, such as the tumor or brain tumor that I was referring to. You isolate and sequence the individual cells. What comes out of the experiment are these reads, and these reads are mapped to a particular position in the genome. So say gene 1 in cell 1. For a given cell, I can count all the reads that map to gene 1. And then from there, I record this in a matrix. So along the rows of this read counts matrix, I have gene 1, gene 2, gene 3, and on the columns, I have cell 1, cell 2, and cell 3. And then from there, we can do a lot of great things with this count matrix. We can, for example, compare the expression profiles of single cells, either using a heat map or some kind of dimensionality reduction, such as principal components. And there we hope to discover new cell types or figure out if there's more of a continuum of cell types. And a common question you might ask with this data is, for example, can we identify changes in genes that are expressed, that are associated with differences between healthy and cancer cells? And so to do that, if you might ask, what does a healthy cell even look like? How do I know what I expect a healthy liver cell to be? Well, or how do cell types change across tissues? Or how does a cell change over time, for example, going through embryonic development? Well, there's an organization called the Human Cell Atlas, and they have a mission to create a comprehensive reference map of all human cells as a basis for both understanding human health and diagnosing, monitoring, and treatment of disease. It's a very large worldwide organization that's producing essentially a really, really big reference map of all cells in the human body. I'm not going to go into too many details, but this is essentially one way that we are going to be able to, for example, if I'm an oncologist treating a cancer patient, if I want to do single-cell RNA sequencing on a tumor from my cancer patient, I can compare the cells from the tumor to some kind of reference map. What do I expect brain cells from a healthy individual to look like compared to what the cells come from that I have, and trying to figure out what the differences are. So this is really exciting. But one thing I just want to note is that they wrote a white paper in 2017, and in it says they expect over 10 billion observations or cells by 2020 as kind of the starting point of this reference map. And what that means is that's a very big data set to try and process as a statistician or a data scientist. And so one of the challenges that I wanted to just highlight from my work is being able to scale up to millions or billions of cells. So being able to write methods and software that can do that. Now, when you start to think about that, immediately there might be this trade-off that shows up in your mind. There's this trade-off between speed and accuracy. If I want to make things more scalable in a reasonable amount of time, then I'm probably going to have to lose some accuracy doing so. And I just want to note that methods for single cell data and in general that don't scale are going to probably not likely to be used as data become bigger, because they're just not going to be reasonable to run in an amount of a small amount of time. And I think it's also important to write software and methods that can work with any backend or any backend data format. So whether this is data on disk, or it's such as something like an HDF5 file where you never load the data into memory, or data in memory, or just sparse data, or data coming from databases and stuff like that. So this is is that a 3-minute warning? Okay, I'm gonna assume so. Yes, okay. So this is a really big problem. For example, I pulled 4 papers from 2019. They all start with 1 million or more plus cells. One way that you can try and perform, for example, unsupervised clustering of single-cell RNA-seq data, or just in general of observations, is k-means. And k-means turns out to be not that scalable. So there was an algorithm introduced by Scully in 2010 called mini-batch k-means. And the idea is at each iteration, you use just a random subset of the data. And this is what I have been working on, or one project that I've been working on to make data scalable. So we wrote an R package along with my collaborators called mini batch k-means, and I just want to highlight the coolness of it. So compared to k-means in red, comparing to mini batch k-means with data stored on disk in blue, we are far more memory efficient as we scale the number of cells from 75,000 to 1 million, with the y-axis being the memory usage on the left and the time on the right. And so we're also not only saving memory, but we're also being able to cluster cells in a much faster amount of time. And while there's no reason, and there's no real reason why this couldn't be used more broadly outside of single cell, basically anything that you would use for k-means, you can use for mini batch k-means, but our motivation was for single cell. And then the last challenge I want to talk about is education. So how do you analyze single cell RNA-seq data? So I frequently hear this when somebody asks me for the first time, I have new single cell RNA-seq data and I don't know really what to do. I wrote a paper to essentially address that. So I wanted to write this paper to help users and researchers navigate the world of single cell bioconductor ecosystem of packages. It's a very rich system. I'll just leave it there in case you want to check it out. But we cover, for example, standardized ways to store single cell data. For example, the single cell experiment object is an S4 object that can have any matrix like object as a backend. So whether it's HDF5 files or data stored in memory or sparse data, it's really cool. We talk about bioconductor workflows. But I think the most exciting part of this project was this online companion book that has really taken on a complete life of its own. It's written in Bookdown. It's compiled on a regular basis to make sure all the code works. It has an enormous amount of philosophical discussions, mostly by Aaron Lunn, a gentleman by Aaron Lunn, about single cell analysis. It's truly cool. Most importantly, lots of R code to help you analyze your single cell RNA-seq data. And this is my last slide. I just want to leave you with a sense of how all this might be useful and where genomics is going. So as I mentioned, there's been a transition in the world of genomics from going from bulk to single cell RNA sequencing. But there are now recent advances that can capture gene expression in a spatial or 2D plane. And this is really useful because you can now identify where the tumor cells are and see how they're communicating with, say, immune cells that are sitting right next to it, because you know the 2D space of where these cells are sitting. But soon we're going to be able to reconstruct the original organ itself in a 3D plane, and maybe in a 4D plane as well when you include time. And I think the combination of advances with these experimental technologies, going from bulk to single cell to spatial to 4D, for example, with the combination with advances in scalable, accurate, reproducible methods and software using R and Bioconductor, makes this a really exciting time to be working in. And I think this is a very important step as we go towards human health. And I will leave it there. Thank you, everyone.
Thank you, Stephanie. Thank you, Stephanie. Yeah. You can be back in video too.
Okay, should I stop sharing my screen?
Okay, yes. Okay, thank you. Thank you for, I really loved the Lego analogy. I began recently to work with single cell RNA-seq data. I'm not an expert actually, but I was an expert in Lego, so I definitely have to switch to that.
I'm so happy to hear that.
I like it. So I'm going to share my screen with the Slido questions that in a moment here. Okay, so we have a winner. We have a few minutes, maybe something like 10 minutes for questions from the public. I would start with the most popular here. Can you comment on the integration between Bioconductor and Tidyverse? So that's a topic. Are there efforts to align these two frameworks?
Yes, there are actually. So I blew through it and I took out the slides from my presentation. For example, there's the Ply Ranges package by Stuart Lee, Di Cook, and Michael Lawrence. And the whole point is to be able to make genomic data analysis more human readable by basically borrowing all the wonderful ideas from dplyr and the tidyverse, but just bringing it in for objects that Bioconductor is used to. So that's one way that it's happening. I would say that if you are, so in my own day-to-day work, I'm often exploring data using the tidyverse itself. For example, being able to make plots really easily. However, there's a lot about genomic data analysis that depends on matrix multiplication. So the objects that somebody might be using in genomics is not necessarily the best way to format that data and store that data is not necessarily a tidy data frame. However, what happens is usually after you do some kind of genomic data analysis, such as dimensionality reduction, you get to a point where you can store your data in a tidy data frame, and then it's ideal to essentially leverage the tidyverse framework for data exploration, which is what it was built for.
Okay, great. Thank you. Something on a different tone. Do you think the academia is the main environment to work in if you're a student or a professional who's willing to work on this kind of data? Oh, that's a pretty huge, actually.
The main environment,
as
opposed to industry. Does that mean industry or government or a nonprofit? So I'm going to assume that the person is considering different job sectors, and they want to know if I want to do genomic data analysis, is academia the only place you can do this? No, by no means. For example, Genentech in the US, in California, has recently hired a lot of great bioconductor developers to develop bioconductor data infrastructure and packages and be able to support the company, but then also being able to give back to the community. So it is true that I am in academia, but by no means, I think, do you have to be. I think there are a lot of opportunities, both inside and outside of academia, to be able to work in this work with this kind of data.
Yeah, actually, I do think that these two things shouldn't be completely separated. Actually, I mean, it's a nurture thing between the two. And we had also a little discussion about business and opportunities, freelancing, and life science academia. And I think the two things are intermingled. And thank you for this take of yours. Okay, so let's see if here I can slide down. Okay, this is down. Well, this is pretty technical. What is the advantage of k-means over KNN, SNN graph clustering for single-cell RNA sequencing data?
Yeah, that's going to get pretty technical.
Yeah, we can skip to the next one.
Okay.
In your opinion, is single-cell RNA-seq delivering on its promises, or a bit of a hype that will be replaced by less problematic technological developments soon?
Oh, these are great questions.
This is a great question, actually.
Okay, so my opinion is that not everything that we have been doing with bulk RNA sequencing or microarrays needs single cell. So there are a few questions, quite a few questions that are ideal for single cell. And there are some questions, biological questions, that bulk RNA sequencing is more than okay and more than sufficient. And so I think in some ways, single cell is delivering on its promises because it is introducing us to be able to see data on a level that we've never been able to see before. And I'm really excited about new technologies as well, like spatial transcriptomics that allow us to kind of see another dimension as well. But it is true that single cell is, in the large scale of genomics, it's one type of technology. And yeah, it will probably change over time. Less problematic technological development soon. So I think the answer to that is, with every new technology that's developed, there will always be problems. There will always be biases. There will always be technical artifacts in the data, no matter how great the technology is, in my opinion. The biases that we saw in microarray are still, to a certain extent, exist in bulk RNA sequencing, and those still to this day exist in single cell. There are different types of biases, and we've gotten really good at figuring out how to correct for a lot of them, but you should always expect problems every time a new technology comes out.
Yeah, especially pushing the limit, probably it's what we need to advance, and pushing the limit means working on the edge. So that's why there are problems. Yeah. We have time probably for another couple of questions. Well, this is probably a Python user would argue, sorry to say Python in this conference, but that the Seurat is the de facto standard package for single cell. I mean, there's compile. So, but as a bioconductor advocate, how do you feel about Seurat now being the de facto standard package for a cRNA sequence analysis? Can the OSCA pipeline catch up in stage, in usage?
Well, I'm going to answer this question by saying I think the Seurat pipeline is wonderful. I mean, I think a lot of people use it in the way that it should be used, and I think it has a lot to offer. And I don't mean to suggest, or I'm not trying to take away users from the Seurat pipeline. I just I want to be an advocate for Bioconductor to kind of showcase what Bioconductor has to offer. So when you look at Seurat, it's essentially, you know, one big package, and it's not 1,900 packages. It's not, in the world of single cell, there are at least over 100 single cell packages on Bioconductor. And so it's easy to kind of get lost in how all of these packages work together, as opposed to Seurat, which is essentially one package. Now, there are benefits and disadvantages and advantages of both. So in Seurat, it's kind of like, it's harder. If I want to change out the normalization method, if I want to change out a different portion of that pipeline, it's not very easy to do so. You kind of just have to work within the Seurat framework, as opposed to Bioconductor offers a lot more diversity in terms of the types of methods that you can use. And so if you're somebody who wants to kind of explore the data with different types of methods, for example, maybe the normalization that you're using for your data violates some kind of assumption, and you know that in your data, but you want to switch it out. With the Seurat pipeline, it's a little bit harder, but with the Bioconductor pipeline, everything is modular. Everything is allows you to interoperate very easily. Output from one package is easily input from another package, and you can easily switch things out. And so I think it depends on the type of experience that you're looking for. To answer the question about catching up, I mean, I think Bioconductor kind of speaks for itself. I mean, if a user wants to use it, I think that's great. I think it has a lot to offer personally, and this is the framework that I choose to operate in. But similar to the discussion about whether you use R or Python, I mean, you should use whatever you need to be able to extract information from noisy, messy data. And if that's Seurat, that's fine. If that's Python, that's fine. I think Bioconductor has a lot to offer, though. So that was my goal with the talk.
Okay, I see that you decided Python here, and also we had this new question actually, but you already mentioned it's Python, and it's good though. But I would focus your attention on, for instance, this question, the last question. What are the key factors to develop? I had in mind this one about education, and how easy do you feel it is to start with Bioconductor if one is not a technical person? I know that you're involved in a number of education and technical and learning experiences. So probably I wanted to hear your take on this.
Sure. So I really started to use Bioconductor during my postdoc in 2013, and I felt like it wasn't really easy to learn at the time. However, I think there's been a big recognition within the Bioconductor community that that's a big problem, and people are working very hard to change it. So for example, with my own contribution of OSCA, the goal was to be able to make it as straightforward as possible for a user who is not technical to be able to analyze or go from raw sequencing reads to identifying what the cell types are in his or her data, if you're willing to, read this really cool book. And so I think it's becoming easier, and I think there's a really big recognition that this is important for being able to allow new users to come into the community and leverage the power of the software.
Okay, thank you, Stephanie, for your talk, and it was very, very nice. And thank you for also referencing our city at the beginning of the talk. Milan, I've seen the Duomo, that was great, and unusually empty. So that's really, really, really weird.
I know.
Okay, I invite everyone to make a virtual applause. Oh, no, we have the real applause too. That's great. Thank you. Okay, now we have basically a virtual break. We can meet the sponsor, networking together with.
good afternoon, everyone, and welcome to the second keynote speech of e-Rum2020. My name is Emanuela Furfo, and I will be the chair of this session. As you had the opportunity to see earlier with our first keynote speaker, you can ask questions through Slido. Ricardo, who is from the organizing committee, pinned a message with a link to access the website, to access Slido at the top of the events chat. So you can use it to ask questions or to upvote the questions that others ask. Okay, so it is now time to actually invite on stage our second keynote speaker, that is Jared Lander. Jared, please share your camera and audio. Okay, welcome on stage, Jared.
Thank you.
Jared is Chief Data Scientist at Lander Analytics. He's also adjunct professor at Columbia Business School, where he teaches the Introduction to Programming in R course. He's also extremely active in the R community. He's the organizer of the New York Open Statistical Programming Meetup. He's organizer of the R Conference in New York, Washington, DC, and Dublin. And he's also the author of R for Everyone. Is that all correct, Jared?
Yes, it is.
Okay, great. Today he will give a talk titled Applying R at Work, and he will take us through a journey through the different ways in which different industries use R and the typical growth pattern at a company. So I now leave the floor to you, Jared, and I will turn off my camera and I'll see you again in about 30 minutes. I will ring an alarm after 27 minutes so that you can start wrapping it up, okay? Okay, cool. I'm really excited to listen to your talk, and the floor is yours.
Thank you. I'll share my screen. So, good morning, everyone, or good afternoon, as it may be. I understand many of you are in Europe. It's a shame we can't all be together, but at least we could see each other virtually. So, I've been using R for many, many years, and ever since grad school, at least, I've been using R for work. And I understand that can look different for different people depending on how their company wants to use R. So we're going to take a look at that journey. But first, we'll start 10 years ago. We'll go back in time. I feel a decade
to interrupt you, Jared. Can you just turn your camera off?
I just remembered to do
cool.
that.
I'm sorry about that.
Yep. So a decade is about a nice measure of time, so we'll go back about that far. And there was a title war raging. People were arguing, are you a statistician? Are you a data scientist? And people were trying to define the titles. They were saying, are they the same thing? Are they different? Come to today, and there's a similar fight. It's now data scientist versus machine learning engineer. Yet another change of titles for what, at least to me, is largely the same job. There's a new entrant in this title war, AI specialist. Because when you rebrand statistics AI, things get a little more exciting. Stepping back 10 years ago again, there was the language war. We're all familiar with language wars. Back then it was R to SAS. That was the big battle. There were other entrants like Stata, MATLAB, SPSS, some other ones. But R versus SAS was the biggest. Coming back to the present again, there's a new language war. R versus Python. Everyone knows all about this war. But Julia's in there putting up a good fight, making an entrance. And SAS is sticking around, believe it or not. A lot of pharmaceuticals use it. There's some old contracts keeping it alive. MATLAB, for the most part, has gone away, except for people doing real engineering, like building bridges and jets. They still use MATLAB a lot. Let's go back in time again and talk about computing. A lot of what we do involves computing. We're at an R conference, after all. Back then, our laptops could handle just about everything we wanted. In fact, this is the model laptop I had. We had blazing fast processors. They were breaking new territory. Moore's law was still intact. We were getting a lot of RAM, and we had 64-bit processors, so we could address all that RAM. And the data was big, but not so big that your nice laptop couldn't handle it. So you didn't need to go to the grid and do fancy grid computing anymore. Coming back to today, things have changed. Our data is much larger, and our laptops and desktops have not improved that much. They are much better than they were 10 years ago, but they haven't kept up with the pace of data. So we're turning to GPUs, as pictured here, and cloud computing. Thankfully, both of those have gotten a lot easier to use. So let's stick with now. Talk about what's going on nowadays. Who is using R? What industries are using R? This is a non-comprehensive list of industries where I have personally helped use R. You can see here it's a long list: banking, food, construction, manufacturing, genetics, publishing. It's a long list of industries. So how are they using R? How are they putting it to use? We're going to look at industry case studies, use cases, for just a few industries. And we'll start with pharmaceuticals. This is a big, important industry, and you want to make sure they get it right. This is life-saving stuff. So just a few of the ways they use R. Drug efficacy. You need to know how much compound is needed in a pill. You want to make sure you get that just right so you get the medicine delivered to the patients properly. We're constantly in a battle to discover new drugs. We're getting new ailments, as we're seeing right now. So we need to discover, is the term, new drugs to help people heal. It's very important to get prescription forecasting right. You need to know what demand you have so you make sure you produce enough of the life-saving medicine. And clinical trials, seeing how well the drugs work. Now that's really something. Because you might have heard, but SAS is mandated by the FDA, the Food and Drug Administration. We hear this all the time that you need to use SAS for clinical trials. We mostly hear that from SAS employees, or people who heard it from SAS employees, because that is a myth. The FDA lets you use other tools. Back in 2015, they put out the Statistical Software Clarifying Statement. Nice block of text here, and it comes down to the software needing to be reliable and testable. And R is both of those. So in clinical trials, reproducibility and traceability are essential. You must have consistency, and you need a paper trail. To achieve that, we can combine our Markdown for writing the analysis in a reproducible fashion, our E&V for capturing the package states. This says what version of the package you're using. Git to track the changes both in the code, in the Markdown code, the analysis code, but also the changes in your package versions. And Docker to bundle everything together so it's reproducible anywhere. You put all of your analysis into a Docker container, give it to somebody, and let them run it the same exact way you ran it. So we're at an R conference, so I have to show some R code. And this is an example of using R in the clinical trial process. Now this is a package GS design for designing group sequential trials. Now this code doesn't analyze the data, but you're setting up the trial, see how it should be run. you set some variables like the number of desired events, the assumed hazard ratio, what power you want, and running the gsdesign function will tell you the number of events required to achieve a certain power and how to run it. So we pipe this into GS-bound summary and show the cable, which is a way to show a table in Markdown. And we get this table showing us how you should design the clinical trial. Now again, this is just designing, not analyzing. You can analyze it in R, but I thought this code would be nice to show. And this is a two-stage trial where you do a number of trials and you see, is there a significant result? If so, you proceed to the next stage. And this tells you how many participants you need for each stage. Let's turn our attention to banks. We all want them to be doing good work to safeguard our money. Some of the ways they use R include targeting offers, what products they should advertise to different people, software efficiency. And this isn't just for banks, this is HR departments in general. Let's say your job requires you to use 5 different pieces of software in conjunction with each other, flipping back and forth, using them all. Maybe they should study this and say, hey, this person's using 5 pieces of software to do one task. Make it 1 piece of software, make their job easier. Valuations. It's really important to know how much something is worth. Whether that's an equity or a derivative, you need to know what you're spending your money on. And in the back of the house, there's fraud detection, a mandate for most banks. So fraud detection can take on many things, and it might not be just fraud. It could be a fat finger mistake that you want to catch before it gets processed. You want to see if people are using bad judgment and stop them from making silly mistakes. Or you could be going after criminals. So this anomaly detection, more than fraud detection, fraud is just one type of anomaly, can be done a few different ways. You can use supervised learning, either regression type models or tree-based models. Time series models, because a lot of financial data has a temporal component. And structural estimation to see, does this data today look different than it normally looks? And some common R packages for doing that, and you'll notice I'm not using hex stickers anymore because not all these packages have hex stickers, but GlimNet and XGBoost for supervised learning, and they're similar. And XGBoost not only does trees, it can also do a boosted penalized regression, getting it similar to GlimNet, which implements the elastic net. Fable and Profit are used for time series modeling. And Anomalize is a specialized time series package specifically meant for finding anomalies. Then you have RStan for doing any of this in a Bayesian manner. And what's cool is that Profit is actually written in Stan. So lots of different tools to do this. We'll look at just one example, Anomalize, where you take in a data set, you decompose it using STL, which is a standard time series method. You determine the outliers using the interquartile range method. You recompose everything and you make a plot, and the red dots are the outliers, the anomalies, the fraud or the bad judgment. And then you would put this down into a further analysis and say, how much does detecting each of those incidents of anomalies cost? And is that cost worth the price of investigation? And that's part of what goes into your calculation of anomalies, is balancing that cost. Turning to manufacturing, and this is manufacturing whether you are making metal or ink or medicine or jets. These principles can apply. Manufacturers will be interested in predictive maintenance. You want to know when a machine is going to fail so you can repair the equipment before it fails. Defects cost a lot of money, so you could use computer vision to look at items as they come off the assembly line and determine, are they anomalies? Are they defects? Should you fix them? For a lot of manufacturing, you have to worry about the temperature of the products as they come off the line. So if you can predict the temperature it's going to come off versus the desired temperature, then speed up or slow down the assembly line to accommodate that, that could be helpful. Electricity usage is one of the most expensive components of manufacturing. So if you could forecast in advance how much electricity you'll be using and buy it from a lower cost provider, that could be really helpful and make a lot of cost savings. And production optimization in general. This is really paying attention to your products, and you have warehouses and factories and customers in different places. You need to fulfill orders, so you need to know what to produce, where to produce it, and when to produce it. And that's a huge field of study. And even though it's a huge field, I will boil it down to convex optimization in general. These are problems like bin packing and job shop scheduling. And simulated annealing. This is when the price of your inputs can be impacted by your production. So when you optimize your production, you need to take into account the shifting changes, and simulated annealing is a great way to do that. There are many packages in R for optimization. These are three in particular that I've used a lot for manufacturing processes. OMPR for linear programming. Optimization does a lot, but I particularly used it for simulated annealing. And CVXR, which is this amazing package for general purpose convex optimization. It does linear programming, quadratic programming. If it's a convex optimization problem, CVXR can do it. It's really nice. So looking at an example of what might go into manufacturing, let's say you have a smelter and you need to melt different metals. You can only fit so much into a smelter at one time, but each metal that you're going to smelt has a different revenue stream. So you want to get as much revenue as you can, but you want to fill up the smelter as much as you can. You can only put so much in there. You can't pack everything in there. So I want to find out how many units of each metal can go into the smelter. I have my cap of how much it can hold. I have the amounts each one is worth, and I have how much space it can hold, for how much space each one takes up. Now this is essentially the knapsack problem. CVXR makes it really easy. You declare the variable that you're going to use to optimize. You put in constraints like the volume of all your amounts can only be up to a certain amount. You can't have negative amounts. You then specify your objective, the problem you're trying to solve. In our case, we want to maximize the revenue subject to these constraints. And you solve it, and it tells you how much of each metal to put into the smelter to maximize your revenue. Now, of course, this is a simplified example. There's many more considerations you need to think about, but this is a starting point. The insurance industry is really interesting because they went quant over 100 years ago, and actuaries tend to be really great statisticians. And they do a lot. I can make a whole slideshow about actuarial sciences. But that actuarial sciences is a big part of what they do, making these contingency tables. And actuaries nowadays, they get tested on R. It's on the actuarial exam. I know this because my book is required reading for them. And remember, they went quant all those years ago, so they want to automate all this reporting. This is a big part of their job, these reports. They built this whole system around these actuarial tables, or it was meant so that humans can go look up the tables and do their work. And we want to automate this process so they can catch up to more of the modern methods. And a sample workflow for this would be connecting to enterprise data warehouses because they have a long history of a lot of data, generating those contingency tables, and they had to build a whole workflow around this, write up their reports, and publish and distribute their work. A standard workflow that a lot of us have with specific needs for their industry. To accomplish this, they would turn to DBI for reading from the database, mortality tables or life contingencies for building the tables, our Markdown is Shiny for building the reports, Drake for composing all these steps together, and Drake could be used in any of these industries. And then RStudio Connect for publishing it and sharing. So looking at the example of Drake, you build a plan, and each of these steps are different steps you need to take on your data. And each one is a function. You apply a function to an object. We read in the data, we build the actuarial table, we generate a plot, then we use that plot and the table in the Markdown report, which can then be distributed. And you make your plan, and then you make it. Only parts that haven't been ran already or haven't been updated get ran. So if the first 4 steps have already been done, and it's just the 5th step that needs updating, Drake intelligently does just pieces of it and orchestrates everything together. Advertising. They have been using data for decades. Now they use R to do A/B testing to see is one version better than another. Targeted advertising. This is true for traditional advertising, but especially so in digital ads. Sometimes you want to use causal analysis to figure what caused something. Someone did this, and that caused them to do this other task. And funnel analysis. How customers progress through the sales process, how they go from one stage to the next. You would want to create a cohort of customers, say these customers all came in the same way, the same time, and follow them as they progress through the buying process. And see how many of them make it from one stage to the next. Because not everyone who comes to your site will go ahead and register. Not everyone who registers will purchase. And you want to see how they progress so you can figure out where to get the kinks out of the process. So you would use the dbplyr package because the data is typically huge, stored in a database. So you would use dbplyr to have a tibble point to a database table, and funnel join, written by Emily Robinson, to figure out how to join together these different tables based on both an ID and time. So look, taking straight from the vignette, we have 2 tables: when a customer landed on your site and when they registered. That's the conversion. And we want to join these based on the user ID, but also making sure that you get the records of registration that occurred after the user landed. And so the after inner join function from the funnel join package does this for us. It joins the tables on IDs and makes sure that the right-hand table, you're only keeping records that occurred after the corresponding records in the left-hand table. Now, all of these industries have similar usage patterns. They have the same typical stages of R at work. And regardless of industry, most companies progress along the same path. First up, you have your maverick user. This is the first person to start using it. They tend to be enthusiastic about R. They're going to the meetups, they're reading R bloggers, they're really excited. They're most likely using R on a Windows desktop. They're not using Linux. They probably have a Windows laptop from work. And they're using R as an Excel replacement. And they're more productive than everyone else using Excel. And they're doing data munging and fitting models, and they're really doing cool stuff. After a quick bit, they form an R study group. This is a handful of employees who all use R together. They are enthusiastic users. They have a Slack channel for getting R help. They have another Slack channel for sharing R memes. And they're certainly collecting hex stickers. And they're really, really excited. And that's the important part. They're using R, they're sharing it with each other, they're getting everyone else excited, to the point that they bring in outside training. They get corporate training. This is when they've gotten buy-in from the higher-ups. The managers, the executives have said, R is looking great, we want to build this process. So they bring in an outside instructor to come teach a few days, a few weeks of classes and get their employees trained up really well. This speeds up the adoption by other analysts who want to get into R. And these early adopters, they get really excited and it accelerates their capabilities. So the next common thing is to get the R server. You're graduating from Windows to a Linux server. This is a centralized, controlled server for everyone to use. They're all using the same machine set up in the same way. They're using Git to version control all of their code. They're using projects. Often they start with RStudio Server Open, the free version. They're just getting their feet wet. And eventually many companies graduate to RStudio Server Pro and Connect. It gives them extra features that enterprises typically want. And they're using project package libraries. This is how you avoid dependency trouble. You have each project you do has its own set of packages, and you could track them in time using R, E, and V. So you have this R server. It's now time to productionalize your code. You're going to put this into production. Then you get told, but you can't put R in production. Only Java and Python are allowed. Nothing else works. It's impossible. Of course, this is a myth. It's just that some people in charge of production systems don't always want to learn something new, so you might have to do it yourself. So you're going to do this properly, and you're going to use a build tool like Make or Drake. Make is general purpose, Drake is specifically for R. If production systems can't interface directly with R, you expose the functionality as an API using the Plumber package. To make sure that your code for production can be repeated if something goes down, you want to be able to go back to the same environment, you're capturing your package versions with R, E, and V. This way you want to build it again, you go right back to the same versions, don't worry about dependencies. And you're going to package that all up together into Docker containers. This way you've recreated the system environment, the R environment, and you have all your analysis in there in this one self-contained unit. And then you can orchestrate that using a pipelining tool like MLflow or Kubeflow and make each step of your process a separate Docker container that flows together and works from end to end, all within R, all meeting production guidelines. That in itself could be multiple talks. And of course, you're going to use CI/CD to automate all of these steps. You write code, you push it to your version control system, whether it's GitHub, Bitbucket, GitLab, whatever it may be, and continuous integration kicks off, building out, running the code, building packages, creating the Docker containers, and inserting into MLflow or Kubeflow. You've built everything end to end, and it all just works automatically now. So, it has never been easier to use R at work. We're in great times right now. 10 years ago, using R for work was harder and easier in some ways. There were institutional roadblocks. Sometimes they didn't want you using R. There could have been an ingrained culture of Excel or maybe SAS. And there was resistance to open source in general. And many of the tools we have now weren't invented yet. So you'd have to roll this yourself, which could be daunting. But the positive was that everything could be done on a single computer, which is really nice, made life easy. Nowadays, though, it is much easier to use R at work. Companies are very open to using R. And open source is everywhere. Everywhere you go, people want to use open source. Sometimes some lawyers try to tell you not to use open source, but the company wants you to, so you work it out. But open source is prevalent. And programming is the new Excel. This is becoming the new literacy. All the analysts are going to need to program. The downside is with the larger data, you need bigger compute. You need to use the cloud or a cluster. But fortunately, it's easier than before, and there's a great ecosystem of packages to help us do that. So you have to ask, what is your use case? What is your industry? What is your business? And you can go to CRAN task views to help figure out what packages to use to help accomplish your task. Then you say, what is your first project? What do you want to do first? You need to tackle something that's easy to show early gains, but it needs to add value. This way you get continued investment. Then you got to ask yourself, what is your end game? Where do you want to end up? What do you want to do? Do you want to have everything automated end to end? How do you want this working? What is your goal, and build your way there. You can't be tempted just to sprinkle AI dust on the problem. So many people think you just use AI and everything's solved magically. It doesn't work that way. You have to plan and build, put in the effort, map it out, and get it right. This takes work, but it's easier than ever before. And importantly, you should use R anywhere and everywhere. Any chance you get, I'm using R for everything. Thank you very much.
Okay, thank you. You actually finished a couple of minutes before. Okay, so we were collecting questions in the meantime, and thank you very much for your speech. I really liked how you went through the different types of people who work with R. And I really like that, and how you spoke about the change in how industries actually look at open source and R. I guess you actually experience that in person, right? In first person.
Many companies. We help many companies progress along this pattern.
Okay, let me just share my screen where I can share all the questions that came through. Of course, more are coming through, so we may start from some and then. Okay, can you see my screen?
It is small. Let me see if I can make it bigger. I cannot. All right. So that first one is obviously a very loaded question. What do I think is going to win the war, R versus Python? In war, nobody wins. Now, it's interesting. So I am liking this, our current state right now, to, unfortunately, our VHS versus Betamax, where Beta was the better tool, but VHS was winning because it gained popularity for certain reasons. And unfortunately, I feel like R is the better tool, but Python is winning because it's more popular. You have a lot of Python people shouting, if you don't use Python, you're not a real programmer. That said, there are so many industries using R for real serious statistical work. If you have a place where they really want to do real statistics, I think R is still going to be around. I think it's going to end up being a stalemate for a long time until some new language comes along and obliterates everything, and we're writing interpreted C because it's fast and easy. I know interpreted C exists now, but I think it's going to be a stalemate for a while.
Oh, okay. Thank you. You're really passionate about that.
Oh yes, and I reined that one in.
Can I just ask you to stop sharing your screen?
Absolutely.
So that we just have one and everyone is focused on that one. Thanks.
Yep.
Okay, so I'll mark this one. Okay, then you can. So these are the most voted. We can go through those, or here you also see the latest questions coming. So I mean, we can pick any of these, but I guess we can.
Okay.
Keep going with the most voted, and then we'll then pick the last one when we have just 1 minute left.
Okay.
Yeah, so about teaching R, I mean, real world R projects. Which approach do you use? That's
so case studies from some of the fields. So it's interesting. So I teach in the business school. And some of my students have asked, can you bring us business examples? And I spoke to some other actually business school professors, and they said, it's good to have just a general purpose learning of it. So I try to bring in interesting data sets, and there might be a business data set, but it might be something about, you know, football, American football, or it might be something about pizza, something that gets people excited. The pizza data sets always get people really excited. So I don't necessarily go for case studies for a specific field so much as something that gets people excited. And for certain people, that is their field. Like we did a corporate workshop for a news outlet, and they wanted stuff that was relevant to their employees. So we managed to cook it up, and they got really focused. But I generally just try to do whatever gets people excited, regardless of the field.
Okay. I would like to go to the this second one here. Then we can go back to the one that is at the top right now. But I know you haven't tackled this in your presentation, but as you're doing a lot with a pretty big community, which is our community in New York, I would like to, I mean, if you have any tips for for people managing local communities, either as big as the New York community, but even smaller, if you have any tips that way.
Yeah. People ask me that a lot because most communities are starting out. They're like, we have more people attend a meetup than are in the community in general in a lot of places. And part of that's because we're in New York and it's a major city, people pass through. We've also been doing it for 10 years. And so I always say to people when you're starting out, there's a few things that are really important. First is make sure you have consistency. Meet every single month. Don't skip a month. This builds a cadence. People have something to look forward to and you have consistency. Also, don't have the same person speak every month. It might be tempting to, if you're the organizer, you're the only person around who wants to give a talk, you just give the talk every month, but you need to have different people. You need to give that sense of community. And speaking of that community, I know from the beginning when I started attending, over 10 years ago and up till now, it's about the people. We had actually, someone told me, a few different people say this, that they don't even use R, they just come because they like the community, they like the people. And a big part of that for us has always been, we get there early and we have pizza. Yep, pizza's a big thing. Sometimes we have drinks beforehand and we have socializing. It's not networking, it's people developing relationships, forming friendships. We have an hour-long talk, and then we go to the bar. And whether you drink alcohol or you don't, you just come and you hang out and develop friendships. And I really think that's the crucial thing you can do, is the socializing and having people talk to each other and getting along and developing these relationships. So social before, social after, with good content in between.
Cool. That's a really good advice. Thanks. Okay, we can continue with the most important.
Sure.
Yeah, I mean, you can pick any of these if you like.
Well, you can see the screen a bit easier than I can, so if you want to pick up what you think is cool, but I can also lean in.
Okay, so how do you think we can promote the data science culture in our workplace? Do you have any tips about it?
It's all about excitability. Do something, a small one-off thing that's maybe outside your typical job description and show people it. But it can't just be something boring. It has to be something that gets them excited, that saves them money, that makes their job easier, and show them, hey, look at this cool thing I did, and look how easy it was. I did a project for a professional sports team here in the United States. And in the first meeting going into it, someone on the team said, hey, can we do this thing right before? We were in a coffee shop and said, can you do this analysis before we go into this meeting? Because that'll really get us good leads. And it's something they have been trying to do in Excel for months. And in about 15 minutes, we did it all in a few lines of our code. We walk in there, we show them, hey, look at this, these 3 lines of code, and look at this, what we just accomplished that you've been struggling for months. And that got them going. So a quick early win on something exciting.
Okay. And again, it seems like it's a bit like community, like getting people engaged and creating relationships, right?
Yep, it's all about people, no matter where you are, whether it's a business or the meetup, it's the people.
I think we have time for one more question. Okay, so we can go for the most. We still have like 15 questions. So actually, sorry we can't go through all of them.
If there's a way for me to answer questions afterward, I'm happy to go into like a room or something if that's what people want.
I don't think we have that planned.
Okay,
Unfortunately.
sure. People can contact me.
Exactly, yeah, they can reach out to you anytime. And you can, yeah, that's a little bit early for you, I think. But during lunch breaks, we have these thematic lounges. But it's like from 1 p.m. to 2 p.m.
Oh yeah, I won't be.
Yeah, that's a bit too early. But I mean, actually, anyone can reach out to you through Hopin with like with private chatting or private conversations. So, or we can keep these questions and discuss them during our thematic launches, though you won't be there, but we can use them as a as a way.
Because I'm on Twitter, Jared Lander, Twitter, and jaredlander.com. People can reach out. If you have like a last good question, you know, it's hard to choose.
Yeah, it's hard to choose. So I'd go for the most voted one. Regarding R in production, do you have any thoughts on proprietary solutions like Microsoft Art Server, which can run R within an SQL server?
Yes. So I've been a long-term partner of Microsoft before that revolution, so I want to put the disclosure out there. And I will say that the R integration to SQL Server, and of course I just gave that disclaimer, I think it's one of the best things they've ever written. It is amazing. I had this one customer where they had a SQL query that was fitting a regression on a rolling window of 144 sliding points. It's taking 10 minutes to run, and it ran multiple times an hour. And I converted that to R code, which ran in SQL Server, and it ran in a fraction of a second. I think that's a great way to do it. I think it's amazing. Now, there are other tools from the tidy models, people like Max Kuhn and his whole team. They have a package, I think, called Tidy Predict, which will translate your R model for some models, mainly linear models and maybe some tree-based models, into SQL code. So you could do that on other databases. That said, the Microsoft SQL Server integration, it just works so nicely once you get the hang of it. So I am a big proponent. I do believe in open source. You need to have an open core and some commercial products around that to keep sustaining everything. So, and they just did such a great job building that SQL Server integration. I highly recommend it. But if you don't want to go the SQL Server route, there are open source similarities that aren't necessarily as seamless, but work nice too.
Cool, thanks. Okay, I think we can close the Q&A session here, but actually they're reminding me from the organizing committee that we also have some open launch, which is without moderation. So you just enter and you talk with whoever is there. And that's open right now, and it will be until the end of today's event. It will be open to tomorrow, until the end of tomorrow's event, and so on. So, so you can still join that and keep discussing. I'm sure you will find many people to discuss there. So now you sort of obliged to go there.
Is that under sessions? Is that, do I find it under sessions? Is that where it is?
Yeah, exactly. It's in the sessions.
Okay. I will go there and I'll stick around for 20 minutes or however long it takes to answer the questions, and happily chat with people.
Yeah, sure. Okay. Thank you again. We were having a big applause at this time, but we had some technical problems. So unfortunately, we cannot send it, but I'm sure everyone loved your speech, and yeah, we've got so many questions and many feedback in the event chat, so feel free to answer those and continue the discussion. Okay, thank you.
Thank you. I'll be in the lounge. Thank you very much for having me.
Thank you. Bye.
Bye.
Okay, so I'll also stop sharing my screen. Okay. I now, okay, so today, the first day of e-Rum 2020 has come to an end. I'm really happy that everything went smoothly, or as smoothly as as possible. And I will now call on stage Maria Chiara Fortuna, who is the chair of the organizing committee, and she opened today's event, so I'll be happy if she closed the event. Sorry.
Hi, thanks, Emanuela, for introducing me. I'm also very happy to be here and to close this day. I'm very happy that everything went so smoothly and well. We made it, actually. I really want to thank all the speakers that were here today. They were actually, I think, 32. So we had already 32 speakers on stage and on session today. If you want to share the slides, okay, I just want to show you some stats about the day that we had. And so, like, we already, I can try to remember, but like we already had, I think, okay, 1,100 subscription for the 2-day event. And so it was something which is kind of incredible, meaning like we were planning a smaller event, actually. And then for this coronavirus epidemic, we had to change our plans, but this case just opened our event to a really wider audience. And I'm also really surprised and happy to see that really people from all over the world, as you can see from the map, were able to attend the conference, this day of conference. The other stats that you can try to see, I made some screenshots, so I'm not sure this like are the, oh no, it's still the previous one, thank you. Sorry, we had some cooperation for some technical issue that we are having. So we actually had, I think, a peak of 700 to 28 concomitant users. So simultaneously, people that were together using, like attending some portion of the conference. And I think a peak of 383 people on one parallel session. So usually parallel sessions are like some kind of smaller, but like we were very happy to see that like so many people were attending, and already 32 speakers on stage. So I really want to thank all the speakers and all the chairs and the staff which is working behind this event, because I was really impressed for the work that everyone has done. And now let's give a look to tomorrow program. Tomorrow we will have we will start today with the parallel session 5 and 6. The first one will be about our world, and the second one about our introduction and still something about our world. We will have the third keynote of the conference, Francesco Bertolucci, that will talk about machine learning and the usage of machine learning. Then another parallel session. Now I think you are getting used to our work for parallel session. And so we will have, like, tomorrow will be slightly more focused on data visualization and Shiny. So we will have a first parallel session about data viz and Shiny, and then another about machine learning. We will have the thematic lunch during the lunch break will be about building community and diversity. And we will have in the morning 2 recruiting sessions, one from 9 to 10 by SDG, and another always by SDG from 11:30 to 12:30. During the entire day, we will have always active the sponsor exhibitors, the networking area, and the open lounge. The open lounge, like the one where Jared is right now. And then in the afternoon, okay, I can see the next slide. Okay, thanks. Thank you very much. We will have the second session of invited speakers, and the focus will be a little more, bit more on data visualization, on our introduction and machine learning. And then we will have something new, so the Shiny demo session. So you will have the time to familiarize with this other format, still in 2 parallel sessions and in the session area. We will have a short break that we called What If, where we will describe our ideas for the physical conference, so everything that we had to forget and throw away when we decided to turn the conference into a virtual event. And then we will close the day with the last keynote of the day, Sharon Mackley's, that we talk about data visualization from the perspective of a journalist. And so this will be like the program for the afternoon, but don't forget that we open and close every day with a yoga session. So now at 5:30, be sure to join the yoga session that's called Release the Tension of Your Back. So after an entire day on behind the desk, I think we all need to release our tensions, and so be sure to go there. And then tomorrow we will start the day with another session from 8:30, which is called Elongate Your Spine. So this will like close the day, this first day. I really hope to see you here tomorrow and for another full day, very full of content, and hope you enjoyed. And let me thank again all the organizing committee and the staff, which is working behind the scenes to make this event happen, and all our sponsor for providing all the support for making this conference free and open to everybody. Thank you very much, and see you tomorrow.
Thank you. See you tomorrow. Bye.
Bye.
Not sure we're going to...
you.